me just share my screen here. All right, welcome everyone. Welcome to the 4th edition of the Feature Store Summit. And we're actually calling it the Data for AI Summit. So we're moving over towards data for AI as a term, and it's about real-time AI applications, batch applications, and large language models. My name's Jim Dowling. I'm CEO and co-founder of Hopsworks, and I'm going to be presenting the summit. I work at Hopsworks. Hopsworks organized this event, and Hopsworks are the OG feature store, at least in the open source space. We were first out there, and I think the first enterprise feature store. So we've got a great lineup for you today. There's a total of 15 presentations from 20 speakers. You'll notice that there's slightly less than 15 companies listed on the page because Uber are going to give a record 3 talks today. So I'm really looking forward to many of those. We have some speakers coming back from organizations, but 11 of the 15 are new. So we're really excited to hear a lot of new, exciting work that's happening in the data for AI space. I'll go through the agenda in a minute, but before we do, let's just do a little background on the conference. This is, I said, our 4th edition, and we have a record number of registrations this year. So I'm delighted to say we've 43% increase, over 4,000 people from 90 countries, not 190. And we can see that there's a lot of people coming in from, the States and India and all over the world, really. So we've got some spots to fill in here, but in general, I think a lot of the world is very well represented. I think Africa we need to give a little push to, but otherwise we're quite well spread. So as I mentioned already, it's the 4th edition of this conference. It's a virtual conference. We started in 2021, which is a virtual time. We've continued being virtual. But for those of you who aren't familiar with what feature stores are and what data for AI is, it kind of all started when Michelangelo platform was announced by Uber in late 2017, where they said, hey, we need data platform support for building AI applications. And at the end of 2018, Hopsworks came out as the first open source feature store, followed closely by Feast and many other platforms after that. So by 2021, vendors started selling feature stores, and that was the first edition of our conference. And since then, there's been a lot of evolution in the space. So there's been advances in real time for feature stores. We saw in 2022, Hopsworks is the first serverless feature store in 2023. And this year, we've seen a lot of new exciting developments. I mean, there's integration with large language models. In particular, vector indexes are appearing in feature stores. I know at least 3 feature stores, and one of which is Hopsworks, where we have vector indexes being embedded as part of the platform. And that's a really exciting development. It means that feature stores can be the data platform for all your AI. But I thought this year that we wouldn't talk so much about LLMs, because everyone is, and vector indexes, but another trend that's been very significant, which is that the offline store, the historical store of data for your feature store, is becoming the lakehouse. And in particular, this is a very interesting paper by Michael Stonebreaker and Andy Pavlo this year called What Goes Around Comes Around Again and Again, if you want to look it up. But they claimed that cloud-based object storage using open formats, the lakehouse formats, will be the OLAP DBMS archetype for the next 10 years. And we've seen huge changes in the last couple of years where, proprietary data warehouses like Snowflake ensured you kept all the data in it. And then they open up to have lakehouse support for Iceberg tables and Databricks with Delta Lake. And of course, we have Apache Hudi as well. We have all these open standards, and all of the major cloud data warehouses now allow you to store your data outside of their platforms in shared storage on object store in lakehouse file formats. So table formats like Hudi, we have Iceberg and Delta Lake. And what's really exciting, I think, here is that this becomes an easy place to integrate analytics and AI, because one of the main features of the lakehouse is that you separate the storage of your data from how you query the data. So that means that AI systems can access the same data that analytics systems can access, and we don't need that integration at the data warehouse level that we've seen for quite a while. So there's going to be a talk about this, and hopefully you'll get something from it. Another significant event, and this is a little bit of a selfish one, is that I come from an academic background, and feature stores don't. They come from a very much an industrial-driven, needs-based background. So it's been companies pushing out the state of the art here. But we haven't seen a huge amount of work in in academia about feature stores. But this year we had a paper at the leading database conference called Sigmon. It was about the HopSearch feature store for machine learning. And what was interesting, I think, about it is that it introduced benchmarks, and those benchmarks are public. And Dave Patterson, who's a very famous computer scientist from Berkeley, makes this claim that for better or for worse, benchmarks shape a field. And in order for the feature store community to become a mature field, we need some form of benchmarks with which to be able to measure things like feature freshness, term that we use quite a lot. So how real-time can my feature store platform be? But also, if I'm accessing data from a Python environment from my lakehouse, well, what is the experiments and benchmarks and typical queries we have to worry about there? So I think we'll see later on that, temporal queries to create point-in-time correct training data is a workload that's quite unique to this community. And that's something that's included in this paper. But also, of course, then, what type of queries and workloads do we have for real-time AI systems, such as recommender systems? So you'll find a bit more in that link if you want to go to the GitHub repo. It's all open source and reproducible. I'm going to do a little bit more self-publicity before we get started. I have a book I'm writing. It's called Building Machine Learning Systems with a Feature Store by O'Reilly. Several chapters are available already if you have access to O'Reilly's learning resources. You can get a couple of chapters, I think, for free if you go search for it. I think it's available on the HopSearch website. So without any further ado, let's present the agenda for today. We have lots of exciting talks. If you're in Pacific Coast America, it's 8:30 a.m. currently. Welcome and good morning. For the rest of the world, good afternoon, good evening, wherever you are. We're going to have our first talk is by HopSearch, by Raymond Cunningham. He's going to talk about from feature store to AI lakehouse. Going to be followed by Uber, talking about their GenAI on-call co-pilot journey. Airbnb are coming back again to talk about Chronon, and they've open sourced Chronon. It's their feature engineering framework. And then we have Etsy for the first time talking here, and they're going to talk about serving real-time features. We'll have a small break, so you can go get some refreshments. And I'm glad then we'll have Stripe. So we're really excited to hear what Stripe have to say about how they built a high-scale, low-latency machine learning framework with Flink. Then we'll have the second vendor talk of today with Chalk. We'll talk about how they do real-time feature serving for online inference, followed by a talk that we're working on here at HopSearch, which I think is kind of interesting. Is the data model for our feature store, should it be a star schema? And Javier will argue that we should move towards a Snowflake schema data model, which I think is quite an interesting innovation in the space. Then we're going to have Intuit talking about how they built a feature store as a service. A little break, and then we'll move on to another talk by Uber about their key value store in Cassandra that they use for feature serving. TurboML will talk about how they use fresh data for machine learning. We'll have Quix, who are a vendor making a platform for streaming analytics. They'll talk about how you enable low latency fraud detection through real-time feature engineering. Varo Bank will talk about how they build features on their feature-driven approach to smart banking. We'll have another talk by Uber again, this time on scalability challenges in building large-scale embedding feature generation at Uber. Roche are going to talk about their platform. Roche are, as you know, a pharmaceutical company, and how they accelerate feature engineering through generative AI. And we'll have another vendor, Fennel, talking about their primitives for maintaining data and feature quality. And that's the agenda for today. I think it's a pretty exciting agenda, you can agree. Lots of different talks from a mix of companies solving problems related to scalability and real-time and large language models, to vendors providing novel and interesting solutions, I think, in this particular space. So as I mentioned before, I work with HopSearch. We organize the Feature Store Summit. We organize the Feature Store community. There is also a Slack channel, and the Slack channel is where I would ask you to go and ask questions to the speakers. There may be time for speaker questions at the end, there may not, but you'll be able to access the speakers, I hope all of them, on the Slack channel. You'll notice if you're logged in through Zoom that there is an ability to ask questions. There's a chat function, but there's also a question function, I believe, so you should prefer to use the question function if it's there. So the Slack, I can see that there's a link to the Slack in the chat at the top. So if you go to that, you'll be able to join the Slack. Otherwise, just Google, if you're on YouTube, featurestore.org, and you'll find a link to the Slack there. We'll be able to ask questions to the speakers. So we've been organized by HopSearch, but we've also have partners helping promote the event. So Decoding ML, which is a very popular newsletter, as is Real World ML by Pao Bajo. And then, of course, NumFocus, who organize the PyData and PyCon conferences. Excuse me, sorry. So this is where you find our Slack channel. So if you have a phone and you're on the screen, you can scan that QR code, or you can just go to featurestore.slack.com to register there. So without further ado, I'm going to introduce the first speaker. The first speaker is Raymond Cunningham. He's a builder of distributed systems with 20 plus years experience in a number of different startups. Either he co-founded or he's one of the first employees. And currently, along with the HopsWorks engineering team, he's building a best-in-class MLOps platform and feature store to accelerate the delivery of cutting-edge machine learning solutions. He has a PhD in distributed systems from Trinity College Dublin. And the floor is yours, Ray. Share your screen so we make sure everything's working okay. I'll stop.
Just thank you, Jim, for the introduction. Just show my screen on this slideshow.
Looking good.
Okay, everyone can see that?
Yeah, floor is yours. Off you go.
Okay, thanks, Jim. Yeah, and hello to all the attendees and fellow speakers. My talk today really is to give an introduction to the AI Lakehouse and give a little bit of history and some important takeaways when building batch real-time AI systems. Now, the story of the AI Lakehouse is really the story of the offline feature store. And what I mean by that is that we're seeing essentially these two different, the Lakehouse features incorporating a variety of different machine learning infrastructure services and basically AI pipelines that make it really an interesting merging of or convergence of two different areas that have been progressing over recent years. Now, in terms of for the 0.01% of people who don't know what a lakehouse is, you can think of a lakehouse as a way for an enterprise to separate the storage of its enterprise data from the processing or compute of that enterprise data. So in the very beginning, storage was done using Parquet files, and that had a number of problems in terms of updating that in a consistent way, right? So Parquet files was typically stored on some form of object storage, mainly S3, and then people introduced table formats like Delta or Iceberg or Hoodie to tackle some of the challenges of updating Parquet files over time. And with the table formats, you had the introduction of catalogs. And in terms of compute, there was a number of different query engines being introduced, lots of interesting innovation happening in this space, like SQL-based or batch-based query engines or streaming query engines like Flink. And then there's a whole set of tooling built on top of this for users to do analytics and various different type of reporting, etc. But the main takeaway from this is we've seen the separation of storage and compute in terms of data and in terms of query engines. And in terms of the recent history, what on the bottom here of this slide, what you can see in terms of the Lakehouse, Databricks introduced Delta Lake back in 2019, and we had the Iceberg spec from the Apache project. Later in 2021, we had the sort of Lakehouse architecture and then a variety of different query engines being introduced like Dremio, Trino, Presto. We've seen a lot of adoption of Iceberg, AWS Glue adding support for Iceberg. It already had support for Hoodie. And more recently, I think just recently, like last week, you had BigQuery announced support for Iceberg. So lots of very interesting things happening in the Lakehouse space. And in terms of HopsWorks, the history of HopsWorks over the last 5 years, HopsWorks was one of the first, or the first, to introduce an open source feature store. And there was always a question around how is offline data being stored. So in the beginning, Hopsworks was using Hoodie and Hive to do its offline storage. And then over time, there was an internal discussions around should this be pluggable, right? And more recently, in 2024, we've introduced Delta support, and we're in the process of introducing Iceberg. So we see that the table formats are somewhat pluggable, right? So you should be able to plug in different table formats or plug in different query engines so that you can get whatever you need done, whatever type of work you need to get done, whether it be batch, real-time AI, LLMs, Gen AI, etc. Now, ultimately, one of the takeaways from this is that the offline feature store is essentially now a lakehouse. What I mean by that is it should be open. So you should be able to pick and choose the type of query engine that you want to use. And because it's a lakehouse, it's not virtual. Now, the follow-on question from that is how do I go from a lakehouse to having an AI lakehouse? And what we would say is, well, it's simple, a matter of adding an online store and a vector index, and a lot of the tooling and services around that to allow you to do a variety of to build the type of AI applications that you want to build, whether they be batch, real time, Gen AI, streamed, etc. Um, okay, so for Hopsworks, you really have to support different table formats, different compute engines, um, and be able to plug in the type of engine that you want to do for the particular problem that you have. Okay. Now an obvious question then is, well, let's talk about these AI lakehouse architectures and see the implications of how they are done. And so in the rest of the presentation, I'm going to cover two AI lakehouse architectures um, to sort of compare and contrast the different aspects of them and how people have been solving these problems, either batch or real-time AI problems over time. Um, But the key point here is not all AI lakehouse architectures are the same, particularly in terms of real time, right? And we'll get into that in a few moments. Okay, so I think I think everyone has seen or used TikTok at some level, but essentially TikTok has built an AI lakehouse. So TikTok's a typical user comes in, um, is presented with a number of videos, and over time, based on the user's history and context, a variety of different recommendations are being made to that user. Now, the key thing to note about a TikTok and ByteDance, we're talking exabyte levels of data, right? And training is being done um, on in an ongoing basis, and your feature freshness is a key aspect to the user experience. So feature freshness is on the order of seconds, and your interaction with the AI built within TikTok is very super fast, right? Um, Now this idea of feature freshness is key, right? So if you want to step back from this and take some abstractions from the TikTok example, what you have is you have data events coming in. So people's uh, scrolling or swiping, and they normally come into some sort of streaming feature pipeline. I think TikTok uses Flink to write data to their AI lakehouse. And then that data gets read by an inference pipeline to present a new video or a new advertisement to the end user. But effectively, this sort of real-time AI system is doing this in the order of milliseconds or sub 1 to 2 seconds, right? And it's been architected that way because they're the use cases that TikTok want to address. And But we've seen within HopsWorks, we've seen similar use cases from a variety of prospects and customers where they want to achieve this type of real-time responses in terms of feature freshness. Now, an alternative approach, let's say a non-real-time AI lakehouse architecture, would be to do ingestion, whether it be batch or streamed real-time, into your offline store. So into Delta, Hoodie, or Iceberg. And then there's some form of synchronization that goes to the online store and the vector index. So that synchronization can be done using something like CDC, change data capture. But the key point here is the writing to your offline store and then the synchronization isn't what we wouldn't consider that in HubSpot's real time. It can take on the order of minutes. So therefore, the user experience is somewhat impacted, at least in the example of TikTok, where the recent videos that you watched and liked, and if you follow this architecture, they're not being incorporated into your next set of recommendations that you're seeing. Whereas TikTok have deliberately architected their AI lakehouse so that they can get feature freshness to really, really low level so that it improves the user experience. So HopsWorks basically provides a real-time AI lakehouse. So from ingestion, whether it be real-time or batch, we can achieve feature freshness on the order of milliseconds to 1 to 2 seconds. And the way we do this is essentially by using Kafka to basically make idempotent updates to the online store, which is RonDB, and to the vector index, which is OpenSearch. And there are still in parallel to this, there are writes happening to the offline store, and they're kept in sync. Right now, the reason why idempotent updates are on this slide separates like out is that earlier version of Kafka didn't provide idempotent updates, but I think that has changed in more recent versions. Okay. Yeah, so the key point of the last couple of slides is to say that achieving real time is quite challenging, right? And the important point here is the architecture that people have settled on will directly impact the type of AI systems that you can build, right? So if you're writing to your offline store and you're not sort of you're not you're writing to your offline store, but not bypassing that and waiting for that to happen before you synchronize to your online or vector index, that'll have direct impact on how fresh your features can be, and it'll directly impact on the type of experience that you can give to your users, right? Whereas the way HopsWorks is architected, by using Kafka and a variety of other different open source tools, we're able to bypass that very slow process of writing to the store. It still happens, but we can basically speed up the writes to the online store so that you can get really, really super fresh features. Right. Now, in terms of the AI, in terms of the lakehouse, what we're seeing is the AI lakehouse is incorporating more and more pieces of functionality, what we would consider from an MLOps platform. So you're seeing more AI pipelines being incorporated, whether like more Python support and support for a variety of different frameworks. People are starting to introduce monitoring. There's a variety of different AI infrastructure or assets like feature serving, model registry that are being incorporated or merging over time. So the Lakehouse and the MLOps platform are somewhat converging on what we would say is this AI Lakehouse. And you're seeing over time that the that users of the lakehouse or users of an AI lakehouse want to be able to do use different query engines for the task at hand. So they want to be able to use Spark because they've already built certain batch systems on Spark, or they may be using some Spark streaming. They also want to use, maybe their data is not so large and they're using DuckDB for doing really quick exploratory data analysis. They could be using Polars, they could be using Dremio. So they're basically plugging and playing the particular query engine that they want to use for the particular problem that they have. Now, in terms of how HopsWorks is architected for this AI lakehouse, everything in green here is what HopsWorks provides, and everything else can be plugged in via. We see everything else as being something that can be plugged in, right? So we have at the very bottom, we have a variety of infrastructure services. We have a vector index, we have a feature serving, model serving, etc. We have a data and model monitoring. We support a variety of different table formats, different storage, whether it be S3 or ADLS. We have a HopsWorks query service, which is essentially an AI query engine. We have very good Python support with Polars, Pandas, GenAI, etc. And you can still use and bring the particular tools that you want to bring to the party. So if you're using Spark or BigQuery or Snowflake, we have support for that. Now, if you want to learn more about the AI Lakehouse, you can go to this blog post that's linked here at the bottom of the page, which sort of explains in greater detail how the AI Lakehouse is done, things that you need to be aware of when building various different systems, particularly real time, when you're solving your particular AI system problem. Now, last but not least, we haven't really, as Jim mentioned, we're not really focusing on LLMs, but that doesn't mean we don't provide support for LLMs. And I'd be happy to, at the end of the talk, to like on Slack or on Slack to answer any questions. But effectively, HopsWorks provides very good support for LLMs. We allow you to do a retrieval augmented generation. So, and any data that comes in that you can pull out the latest data from your offline store or for the online store to augment the user experience with the history and context that we sort of covered, we touched upon when we talked about TikTok. So that can be easily done with HopsWorks by building RAG in from the very get-go. You can do function calling, so you can pull data from your offline store into your pull offline data, pull data from your offline store to augment your generation of recommendations. And also you can do function calling to do training, right? So that's basically everything that I wanted to cover. So if there are any questions, I can take them, or I can pass it back to Jim.
Thanks, Ray, and thanks very much for keeping time. I think everyone appreciates it. There was one question in the chat. I think you can probably answer it by typing it, but maybe we can have 1 minute to take it. It says, in addition to real-time AI, I'm keen to see architectures for on-demand feature creation from external data. So I guess, is there any support in HopsWorks for on-demand feature creation?
Yeah, so recently we've basically spent a lot of time looking at the transformation functions. And one aspect of that was on-demand transformation. So you can make external calls, like HTTP request calls to pull data from, let's say, if you're building a weather type application in terms of you're building some prediction of let's say air quality, etc. You can pull data from external sources using on-demand transformation functions to
To create features, yeah.
Yeah, to create new features or to augment your existing features. Yeah.
Thanks a million, Ray. We're out of time. If you want to ask Ray more questions, please join the Slack channel, FeatureStore.org Slack channel. You can ask him questions there, and I'm sure he'll be delighted to answer them. So let's move on. Next talk is by Uber. So I'm delighted to welcome back Parth and Nicholas and Edwards for the first time. Parth Shatani is a staff software engineer at Uber AI Gen AI team in SF, and he specializes in building distributed systems at scale. Previously worked in building large-scale systems at Amazon, AWS Chatbot, and Microsoft Teams. Nicholas Brett Market is a staff software engineer at Uber, TLM for the feature store team in the SF area as well. And he specializes in serving data for ML models at high scale. And previously worked on Siri at Apple. And then we have Edwards Sidorovicius. He's a senior software engineer in Uber's AI team, the platform team based in Amsterdam. Before joining Uber, he gained experience working at a tech startup and a manufacturing company where he specialized in machine learning applications. He holds a master's degree in AI from the University of Amsterdam. Thanks for joining us, and please share your screen and make sure everything works, and the floor is yours.
Awesome. Okay, you guys can hear us?
Yeah, I can hear you, Parth.
Okay, perfect. Okay, I'll share my screen. 1 second. All right. So let me know if you can see the screen.
Everything looks good, yeah?
Okay.
Okay.
Perfect. Then we can get started. Thank you, Jim, for the introduction. It's great to be back here. Yeah, it's always that time of the year we look forward to coming back here. So yeah, today we are going to present on our GenAI on-call Copilot journey, how we built it, what all things we went through. Yeah, and we have Nicholas and Edwards with me as well. All right, so this is how pictorially a day of an on-call looks in Uber, and pretty much I would imagine in most tech companies where there is so many different changes happening. Even a small config change can cause an outage, and then there is so many different platform. Like for example, Michelangelo is a ML platform in Uber, and there's so many different components in the platform that can change underneath, and that can cause issues to the customers. So an on-call really has to fight a lot of fires, look at incidents, look at incoming customer issues, and there is like too much to deal with in a day. Yeah. So from a user perspective, the users of platforms like Michelangelo and other platforms, the problem is like users are wanting to develop some products on top of these platforms, and they have to navigate through a bunch of complexity, and they need help from on-call, but then the on-call is busy doing so many things. So there is a lot of loss of productivity in that sense for the users of these platforms, since they have to wait, and pretty much there is so much domain knowledge that only the on-calls have that the users might not be able to troubleshoot issues on their own. Other thing that we also find in Uber, which I would imagine is also generally applicable to most tech companies, is that information which is relevant to what a customer wants is generally spread out in many different data sources. It's like NGWikis, Jiras, and Slack, and Google Docs, and like any other information in slides. This is like all spread out in so many different tools, and there is no one easy way to find out, okay, for a given problem, where to go and look for actual answer. So yeah, we had all these pain points at Uber, and that's where we thought like having a GenAI on-call Copilot should make life easier. But then as we were thinking about building it, we also saw many challenges for it. So here are some of these. With any GenAI solution, the LLM is there in the picture, but then the response accuracy, the hallucination is always a challenge to deal with. So that challenge actually leads to, there is some sort of bias, at least we observed in humans, that our users feel more comfortable when the on-call responds the same answer that the bot would respond. So there is some credibility issue as a bot, even though it responds right. Somehow the human beings feel like, okay, we need more human support in the loop. So there's that issue. Also, building a very clean UX experience, specifically, we'll show it later. I mean, it's a difficult thing to knock down because users expect a lot of features from the bot specifically, and somehow their bar for the bot is always higher than humans. Also, with the LLMs in picture, there are so many third-party LLMs coming into the market, and ensuring or using judgment of which data is okay to be sent to the LLM, that's like requires a lot of judgment. So that's a difficult problem. And then curating which data sources actually have good information, that also requires a lot more work than what we anticipate generally. Yeah. So I'll just show you what we have built, and then I'll pass it over to Nicholas and Edwards. So here is just a quick glimpse of what we have built. So like here, example, Edwards is asking a question on one of our Slack channels. And Genie, our on-call co-pilot, is answering that, okay, what is Michelangelo? Michelangelo is Uber's internal machine learning platform. It's also giving references of where it got the answer from. And then is also giving users ability to give feedback on how the bot did. So idea is that we use this feedback to basically make sure the answer quality can keep improving. That's the whole ecosystem we built. So in general, our objectives are we want to collect feedback. We want to provide really relevant information with sources so that it improves the credibility of the information is not hallucinated. And in general, as you can see here, the user doesn't have to wait for the on-call to respond. It's pretty much instantaneous response, which improves the life of the user and productivity of the whole engineering ecosystem. Yeah. Over to you, Edwards. Over to you, Nicholas, rather. Yeah.
Thanks, Parth. So now I'll talk a little bit about the high-level architecture, and then we'll dive a little bit into each of the components. So at the highest level, our platform architecture provides a zero code solution for managing generative AI chatbots. So all the customers need to do is specify their data sources and integration points through configuration, and our platform does the rest. One of the most common use cases here is for teams to leverage chatbots to answer questions, as we discussed, which they had already documented in their wikis. Take our team Michelangelo as an example. We may receive a question such as how to train a model, and these steps are clearly laid out in the existing documentation. So all our team had to do was configure Genie, telling it which data sources in Wiki to use for our help desk channel. And that's why first and foremost, the platform provides two primary APIs, one data ETL to regularly refresh your data, and two, the chatbot APIs, which integrates with LLMs to provide the quick answers from your data. So creating a POC with all these tools, like in a Python notebook, is one thing, but productionizing a platform has a lot more baggage, which is why we also cover evaluation and cost tracking in our solution. These additional features help users understand and address issues in data quality. And as we know, bad data in and bad answers out. And then with Gen AI usage quickly becoming one of the highest ticket items on budgets, cost tracking is a must. Next slide, please. So first we'll talk a little more about data ETL. Here our goal was to make it as easy as possible to integrate customer-specific data from the most common data sources. That's why we brought this experience directly into Michelangelo Studio's UI. You can see on the right side what it looks like to integrate a specific data source. On the top right, you can see how to set up a wiki, where you just need to provide the wiki spaces that contain the relevant pages. For example, in this slide, the user provided the Go monorepo space and the Go framework space. Below that, you can see how to configure a Slack data source, providing the relevant tags. And then on the bottom right for files, you can just drag and drop them directly into the page. And then their corresponding blob store file paths are displayed for reference to the user. And then here on the left side, you can see kind of end-to-end what it looks like. Customer would enter in like the name for the pipeline, select the multiple data sources where they want to write the data to, such as a Hive table or to a vector database. Next slide, please. So now let's take a look a little more closely at how the data ETL runs step by step and some of the customizations we allow. So we start with a daily pipeline trigger, which kicks off the process. Then the pipeline consists of 3 major steps. First, data prep, then chunking and embedding, and finally pushing to external systems such as Hive or a vector database. In the first step, data prep, the pipeline pulls data according to the user's configuration. With semantic search, one of the easiest ways to improve accuracy is to narrow down the scope and difficulty of the problem. As such, we usually recommend users provide only data which is directly related to their problem. Otherwise, noise in the data could degrade accuracy. The second step is data transformations, both chunking and embedding. We have default chunkers based on the data sources and file types, but any custom chunking can be added as well. For embedding, we offer 2 primary methods, first being proprietary API calls such as OpenAI, which many customers use as the default, and second, open source models. We've seen open source models, they've proven to be accurate and cost effective, particularly for higher scale use cases. These models are hosted in Michelangelo and can be used for the latency sensitive online serving cases, as well as batch high throughput offline pipelines like this one. Finally, we come to the pusher step. Here we integrate with vector databases as well as offline storage systems. Offline storage systems give us the ability to easily inspect and reuse the data. You can use regular SQL tools to debug and analyze the data. Also, if the upload to the vector database fails, it provides the ability to retry uploads without rerunning the entire pipeline. After being persisted offline, the data is then written to an online vector database where it can be used for online serving. Now I'll hand it over to Edwards for the rest. Thanks.
Thank you. So yeah, this is the overview of the platform, how we managed to receive the question and then eventually respond to the question. So it all starts pretty much with the user posting a question. And in our case, mostly Slack. It also can be ID or maybe something else eventually. And then this question is eventually posted to knowledge base service. And this knowledge base service has 3 steps: embedding generation, context retrieval, and answer generation. And the first embedding generation, we have to make sure that we use the same embedding model which we used in data ETL. Then as soon as we retrieve the vector of the embedding of the question, we pass it to the context retrieval. There we use either similarity searches or any other searches to find the most relevant context. And that context we pass to the answer generation. There we add prompt, ask LLM. Again, it could be open source, self-hosted, or OpenAI or any other proprietary model. And then eventually the answer from the LLM is given back to the client. And there are 3 main features which makes this platform interesting. First is we managed to include the cost tracking in the platform. So how it works is that when the customer asks a question and then this user experience or Slack channel, for example, it also passes the ID of a Slack channel, and which is kind of ID of a customer. And that ID is then propagated to all the LLM calls in the logs. And then these logs eventually can be parsed. And then from that, we can make a dashboards and then we can attribute the cost, who and how much spent on the calls. Another thing what we wanted to make sure is that we allow customers to have custom prompts, because everyone has their own prompts and they think that one is better, one is worse. So in the answer generation step, we actually call key value database where a customer can manually keep their custom prompt, and that prompt will be retrieved in the answer generation step and added to the prompt and then eventually given to the LLM. And in this demo slide, you saw that it also gives the citations. And to enable the citations, first of all, when we did the context retrieval, we make sure that we keep the link and we pair it with the chunk, and then we pass it to answer generation. We build the prompt such way that we pair the link and the chunk together, and then in the prompt itself, we also want to make sure that LLM returns what is link, what is the source of the context which you used, and yeah, it works pretty well. Next slide, please. And then yeah, like when you put it to production, then you obviously need to have evaluation to make sure that it works well. And this is another extra pipeline which runs. And then for that, it also starts pretty much that we retrieve the data from Hive tables. We retrieve logs. And the logs is pretty much where we keep the question, answers, and the context. We use user feedback from the Slack. And then, yeah, because we don't want to run this evaluation on good answers, we want to make sure, like, we want to understand why, when it's wrong, why it's wrong. And sometimes we also use some extra metadata to eventually group the results. And all this data is passed to the feature prep. And feature prep, the data is retrieved, joined, cleaned, and then it passes to evaluator. And evaluator runs on every question answer pair, and there are two ways to go with it. Like one is classical NLP metrics, like Blue Score or something else, and then we can again use LLM as a judge. And what we find interesting in this case is that we were asking like for a coverage, we were asking, is this question sufficiently covered in the documentation? And if it's not, can you please provide suggestions how we can improve the documentation? And then, yeah, from that evaluator, we pass it to the aggregator, because typically everyone wants to know like general metrics. And then if it's a numerical, we calculate the mean and whatnot. And then if it's a textual output from LLM as a judge, then we ask another LLM to summarize all the suggestions. And then eventually we put it to evaluation report, which is the UI for Michelangelo. Next slide, please. And this is the UI of Michelangelo. So here you can see that the bottom there was on the question level that you have a coverage score, question, response parts, and then you can see all the context and whatnot. And yeah, you can go through by question level, and then at the top you can see the total summary of the report, how it sums up and gives the general suggestion for everything. And then yeah, next slide, please. And yeah, so far we enrolled the Genie on more than 150 channels. We answered more than 70,000 questions, and yeah, in half of the cases, customers found it helpful. So yeah, there's still quite enough to improve. But yeah, and but anyway, we calculated that we saved almost 13,000 engineering hours, and yeah, so far it's like pretty much one of the main conclusion is that it's easy to demo like any Gen AI application, but when you go to production, then it's always hard. But it is also very important to use to work with the customers, so we can gather the feedback and then improve on our side. And Genie started as one of the first use cases in Uber as a RAG, but then we built all this infrastructure, and now we enable a lot of other use cases to utilize this infrastructure for their own custom RAG applications. Next slide. So yeah, thank you for your attention. Then we recently published the blog about Genie, so you can follow the link and pretty much read more about it. So thank you.
Brilliant. Thanks, guys. It's fantastic. Very fascinating work, and great to see the work on ROI. I think at $100 per hour, that would be $1.3 million saved. My basic math here. And then, of course, you have the info that you can generate more. We're kind of out of time, so there are a couple of questions. You can answer them, I think, in the chat, or go to the Slack channel to answer them. And there's a lot of cool stuff. I'm sure you're going to work. Anything you're looking at, knowledge graphs, cold poly, anything like that you think is the next step for you, or before we move on? No?
Yeah, I think at least, I mean, we have a lot of things in mind. It's also a question of like, I think the ROI is always the question. Like, I mean, where do you put time to really get max bang for the buck? I think that's something we're still like brainstorming on. Where do you put our big bets on? I don't think we have locked down what really we should bet on. But I think all of those knowledge graphs, I think there's many things that we are thinking still here.
Brilliant. And I think, in particular, to see ROI on Gen AI at this stage is really unique. I think it's one of the first times I've heard a good analysis. So fascinating stuff. So we'll move on. Thanks to Uber. We'll have two more talks from Uber under the rest of today. We're going to move on to Airbnb. It's not the first talk from Airbnb, but it is the first talk from Pengu Ho. So Pengu is a senior software engineer at Airbnb. He has over 5 years of hands-on experience in building Airbnb's ML infrastructure. He's a founding member and project management committee, a participant of Airbnb's open source feature engineering framework called Chronon. And that powers many workloads at Airbnb and has boosted the productivity of many of the AI practitioners there. And before he joined Airbnb, he worked at Capital One on their data and ML platform. Pengu, thank you very much for joining us. Can you try and share your screen?
Yeah, let me do that. Thank you, Jim, for the introduction.
Sure.
Thanks for having me.
We've been doing great so far on the technical side, so fingers crossed that it keeps going. Yes, look like we're live.
Okay, nice. So
Thanks.
can you guys see my screen?
Everything's great. Go for it.
Okay, cool. Let's get started. All right, thanks everybody, and thanks for having me. My name is Pengyu Ho. I'm a software engineer at the machine learning infra team at Airbnb. Today we're going to talk about Chronon, Airbnb's open source feature engineering framework. Here's the agenda for today. We will first talk about what is the necessity for Chronon and what it is. Then I'll introduce the concept of point-in-time correctness, and how things were done before in Chronon. Then we will talk about the high-level architecture of the Chronon, and I'll walk you through a few real-world examples. Lastly, I'll wrap up the presentation with some takeaways and our call to actions. All right, let's dive into it. First one is actually, why do we need Chronon? So what are some common challenges before a feature platform for the machine learning engineer practitioners? Firstly, we observed that feature definitions can be scattered all over the places. So this way, it actually can lead to poor interpretability and difficulties with debugging processes. And also due to the scattered configs, AI ML models suffers from the online-offline inconsistency problems. And some of the slow backfills, it can affect the overall iteration speed of the model. Backfill could be arguably the most time-consuming process during the overall machine learning workflow. And we also observed across the orgs that the AI ML practitioners have to write similar glue code to manage the data pipelines, and it will have lots of duplicate work across different orgs. So Chronon is here to address those challenges. So what is a Chronon? Chronon is an open source platform enabling machine learning practitioners to efficiently develop, deploy, manage, and monitor machine learning data pipelines. Let's take a look at this spectrum of machine learning applications. On the left side of the spectrum, those are mostly unstructured data, for example, image classifications or natural language processing models. On the right side, we have structured data. Those are maybe credit scores, personalizations, and recommendation engines. On the left side of the spectrum, usually those features are available all at once. It's either a full sentence or just the entire image. the feature engineering work is relatively smaller because you just need to do, for natural language processing models, you just need to do something like removing the stemming words, tokenizations. For pictures, you may just to do some transformations on the pixels. However, on the right side of the spectrum, those data usually arrives steadily as the user interacts with the platform. And the features has to be extracted from multiple event streams. For example, logins, clicks, and page views. It requires very iterative manual feature engineering processes. So Chronon is to actually to simplify the process for this step. Also, with the recent popularity of the large language models, we are also working on unifying the unstructured data and the structured data for the AI models. I also want to share our journey to open source. So the project initially started back in 2017 at Airbnb. We actually iterated over 4 internal versions. And in 2022, we partnered with Stripe for beta, closed beta. Now Chronon is fully adopted within Stripe, and they are also in this summit. They will present Shepherd at 10:10 PST. Please also join them. And in April 2024, we announced open source, and the Stripe is the co-maintainer of the project. Now, let me introduce the concept of point-in-time correct. We have this chart. For the x-axis, we have the time. For the y-axis, we have feature 1, feature 2, and the predictions and the labels. So if you want to compute the features for feature 1 and feature 2, let's say it's a simple operation of a sum. So at the prediction of P1, we should only include the raw events that are prior to the prediction of time P1. So as it shows in this chart, we should only include all the blue boxes from the left side of the prediction P1. So for feature 1, we should sum up 0 plus 5 plus 7. That gives us 12. For feature 2, it's 3. We should not include anything that are after that prediction time. It will cause the data leakage for the machine learning models. Let's take another example. If we want to predict a P2, and this time we have to update our feature values. For F1, this time we just need to add 4 to it, so it gives us 16. For feature 2, we sum up 3 and 2, it gives us 5. And similarly, we should not include anything that are after prediction time of P2. So why is point-in-time correctness important? What are some common symptoms? So it's usually the model will perform really well in the local, but it performs poorly in the production. It is because the fact that in real-world applications, the model could not foresee the event that will happen in the future. Point-in-time correct matters, especially for time series and real-world events. Let's have a quick example. So let's say we're working on a house prediction model. Those the feature can be based on rooms, locations, size, age, etc. But we should not use the features like offers or offers received or buyer's info, because at the time of the prediction, those information we don't know yet. The number of the offers at for a house might not receive until the deal is settled. So we should not use those features from the future to predict the models. Next, I'll talk about 2 common approaches. What was the life before Chronon? First one, let's call it replicate offline to online. So let's say the AI machine learning practitioners, they want to start to train a new model. they will start with a SQL query to generate the training data from the data warehouse. When the model looks good in local after several iterations, now they are working on productionizing the model. At this stage, usually they will have to translate their SQL query logic to another programming language. For example, if you're using Java for your service, it would be Java. If you're using Python or any other programming language, you have to replicate these queries to your production service. So this will actually cause the multiple feature definitions scattered in multiple places. And when you translate usually those two things cannot be the exact same. So it will also lead to inconsistency problems. It will slow down the overall performance. Next approach is log and await. Let's say we want to log a new feature. This time we will have to make code changes in the production, deploy it, and wait. But for this approach, the features are always consistent. But every time we will have to go through the code change, deployment, and wait process. If we are working on some seasonality features, then we will have to wait multiple months to collect enough features to train a model. This will affect the overall iteration speed a lot. Now let's talk about how can Chronon address those consistency problems without waiting for months. So the first is the Chronon way. We will have a single Python config file for both online and offline. And it's using the same Scala computation engine for both environments. And the Chronon will also take care of the infra-orchestration work. So the AI ML practitioners can just focus on their core modeling problems. Let's talk about the high-level architecture of a Chronon. So in the left side of the green boxes, we have the feature definitions and aggregation library. On the upper side, we have the offline. The training data will be written to the data warehouse. On the lower side, we have the serving path. So for both online and offline, it's actually using the same feature definition and the same aggregation library. So this guarantees the consistency across two systems. And it simplifies lots of the work for the AI ML practitioners. And for our online serving pipeline, the project is based on a Lambda architecture. Given the time constraint, I will not dive deep into that. Let's continue to some real-world examples. So this is the feature definition for group by. The syntax maybe sounds familiar to SQL syntaxes, but it's slightly different. Let's take a look at this example. The source, usually we can define it with some Hive tables or some real-time data sources. The keys here is the aggregation key. And next, we can define a list of aggregations. For the same input column, we can actually simplify the aggregation definition process by giving multiple windows to the same operation. So for this example, we are operating a sum, and the windows are 7 days, 14 days, a month, and a year. So the window operations are supported natively in Chronon. And right now we are supporting, I think, 15 operations, and those operations can be easily extended. Next, I will talk about the join. Join is used to answer this question. So what is the aggregation statistics for a certain key from time A to a certain timestamp? The aggregation statistic for a key from time A, those were defined in the group by already. And for the join, we just need to provide a left source. That will be the reference time for these features. Some of the challenges we have to solve for this join is we have to optimize the backfill algorithm to handle data skews. And if your model does not require point-in-time correct, midnight accuracy can be much faster. I want to also share a quick fun fact. One of our users actually achieved with 250 lines of code to define 1,000 features. That's translated to one line of code to 4 features, which is definitely amazing. Next, I want to talk about 2 new functionalities that are widely adopted within Airbnb. First one is derivations. Let's say we want to compute acceptance ratio, that we will use the accept sum to divide it request sum. The accept sum and the request sum can be easily computed from the joins or goodbyes. But if we want to compute the acceptance ratio, then usually we will have, without derivations, the user will have to write this logic in their service. Some of the challenges for those new functionalities are we have to make sure the APIs are uniform for both online and offline, and also to guarantee a low latency online service path. So on the right side, we have an example just for the syntax. We have on the line 6, we have a derivation definition. On the line 7, we have a name for that derivation. For the line 8, we have the expression. It's accept underscore sum divided request underscore sum. And for all the expressions in derivations, they will support the Spark SQL syntax. Now let's take a look at the real-time chaining features. Let's say we want to compute the average price of ice creams a user viewed in the last 14 days. This requires transformations and aggregations along with some denormalizations. It shares the same challenges with the derivations. For example, we need to guarantee the online and offline consistency, and we also to make sure we have a low latency serving. On the right side, we have the example of how to calculate this features. On the line 3, we have the source, and I didn't include the join source here. It's basically just the join between the, for example, the ice cream ID with the ice cream price. Now we have the aggregation key is actually over users. Next, we will create the aggregation. This aggregation, this time the operation is the last K, and then we will say we will collect the last 100 user viewed ice cream price. And the window is 14 days. So after the aggregations, we can write the derivations. This example could be a little complicated, but it's also to showcase the complexity that the derivations can handle. So to calculate the average price for the last 14 days, then we can write a function to accumulate for the past 14 days for the total ice cream price and divided by the total size. Then we get the average price of ice creams a user viewed in the last 14 days. All right, let's talk about the key takeaways. So first one is Chronon is actually a declarative feature engineering framework. It handles both for both online and offline features. We use a Lambda architecture to achieve online-offline consistency and low latency serving. Windowed operations are supported natively in Chronon. And right now we have 15 operations, and it can be extended very easily. And for those operations, we sometimes we will leverage some of the sketch algorithms to address the scalability problems. And yeah. Last is our call to actions. Because now we're open source, you can see our repo at the github.com/Airbnb/Chronon. Here is the Kickstarter. You can report issues or ideas to our Git issues. We also have a public Discord channel for users to discuss problems. Now we're using a Slack, but the link is in the Discord channel. You can join and find it. I have a few additional resources. The first two is Airbnb's blog post. The third one is actually from Stripe, how they adopted Chronon to implement Shepherd. And yeah, last two are just some code repo and some introduction. Thank you. And yeah, thank you for having me. And any questions?
Thanks a million, Pengyu. Great to have Airbnb back, and great to see Chronon being open sourced. I think this has been coming for, actually look back, I think in your first, in 2017, 2018, no, 2018 maybe, there was talk about open sourcing Zipline at the time. And I know it takes a long time at large organizations.
Yeah. Yeah, we are, our team are all very happy about this. Yeah.
Right. There's a few questions if you want to answer them in the chat, or I would jump on the Slack to answer questions as well. But we're out of time for answering the questions live. So thanks, Pengyu. We're going to move on. And the next speakers we have are from Etsy. So it's the first time we're going to have Etsy here at the conference. We're delighted to have you. And they're going to talk about serving real-time features at Etsy. We have Prachi Poddar, who manages the feature store team at Etsy, where she's leading the effort to build the next generation feature system. And prior to Etsy, she worked at Twitter, where she worked on recommendation systems and built several 0-to-1 products, including long-form tweets, interests, and topics. And outside of work, she likes Eastern philosophy and exploring new places. We also have Tiani Kui, who works as a senior software engineer on the feature store team at Etsy and has been on the feature store domain for the last 4 years, which is an eternity in our space. And she's passionate about infrastructure and smooth customer experience in delivering data-intensive products. Thanks very much. And please go ahead and share your screen and make sure everything is in order.
Thanks, Jim, for the intro. Yeah, Tian would be presenting the screen.
Yeah, looking for the screen.
Yeah.
Seems to be lacking some permissions.
So there's a green button at the bottom, screen, or share, sorry, I should say, in Zoom.
I need to configure some system settings, I'm sorry.
Okay. Okay, then while we're getting started, I guess we can just take a brief intro. So Etsy, it's your first time here at the conference. You know, what have you built this from scratch, or tell us a little bit about how this started and when you've actually then ran the feature store in production. When did you manage to get into production?
Yeah, absolutely. So our team manages actually both the real-time and batch feature stores. And initially, the very first MVP of feature store at Etsy was built back in 2019. And since then, at that time, the systems were built for a very small scale. And then Etsy over, time grew a lot. And over time, we had several iterations of, new feature development on top of the initial feature store.
So now we'll hear more about real time. I think we're looking good to go.
Awesome. So yeah,
So off you go.
Yeah, thanks, Tian, for presenting. Let's get started. So greetings, everyone. Thanks for having us, and really excited to be representing Etsy for the very first time in the Feature Summit. So our team, as I mentioned before, basically work on both batch and streaming feature systems. And today we'll be focusing on Rivulet, which is our real-time feature store. So let's look at the agenda. So we'll start with the overview of the system scale and how we handle different types of features at Etsy. Then we'll dive into the Rivulet architecture and explain how we support each step of the feature workflow. And lastly, we'll discuss a little bit about some challenges with our current system and some ideas of addressing them. So let's begin with looking at the scale of our system. So as you may already know, Etsy is a global marketplace for unique and creative goods that connects our community of over 6 million makers, artisans, and creative entrepreneurs to over 90 million of buyers looking for something special. So every purchase on Etsy comes from a real person, and the Etsy's machine learning teams are constantly working to create a better shopping experience that drives more sales to our small businesses on our platform. To support the Etsy scale, our feature retrieval service handles about 200,000 requests per second for batch features and around 160,000 requests per second for our real-time features. The average P99 retrieval latency is about 50 milliseconds. The real-time time series features are available within about half a second of ingestion latency since the source events were fired, and the numeric features are usually delayed by about 15 seconds. So let's look at what kinds of features we support today. So we categorize these ML features into three main types: batch features, real-time fact features, and real-time aggregated features. So batch features are ingested with a scheduled batch pipeline, with both types of real-time features are ingested with the streaming pipeline from the input Kafka stream. So since real-time fact features do not require any runtime aggregation, and thus it does not require tracking timestamped information in the database, we store them with the same schema as batch features. So all the features for each entity ID are on the single Bigtable row, but in different column families and have different column qualifiers. So on the other side, the real-time aggregated features use simple key value schema. Each key is composed of feature name, version, entity ID, timestamp, and a hash of the entity ID prefix, which we use to avoid Bigtable hotspot issues. Speaking about the real-time aggregated features, we support three different types of those. So there are like numeric or count features, which compute things like sum, max, average, and count over a specific time period that we call the aggregation window. Secondly, the time series feature compute a time series of elements for a given feature key. And then heap features are used to represent popular or trending elements for a given key. So now we'll walk through examples. We'll see how each type of aggregated real-time feature is computed, stored, and retrieved. So let's talk about count features first. So let's say we want to build a model to find the most relevant listings for a search query. We may use a real-time count feature that tracks each listing's total view counts in the past 24 hours. So all real-time feature data comes from raw beacon stream. Beacons at Etsy's data infrastructure refers to events or signals that are logged and processed through various pipelines for analysis and tracking. So here's a simplified version of some examples of beacons. From the raw source stream, the streaming ingestion job filters the relevant events, such as view listing beacons with valid listing ID fields to compute the feature values. Then comes the most important transform in the feature ingestion pipeline, which is pre-aggregation step. So for any count or numeric feature, the feature creators can define a pre-aggregation bin size, which is smaller than the feature's total aggregation window. This pre-aggregation bin is used to reduce the number of rows needed for the Bigtable scans and runtime aggregation in the feature service, and further reduces the overall feature retrieval latency. So in this example, if we set an hourly bin, the pipeline rounds the timestamp of each incoming beacon down to the nearest hour and count the beacons per listing for each bin. The pipeline then retrieves the historic values for the bin from Bigtable, merges the count, and updates them back. Now at the retrieval side, when the service sends a feature request for the listing view count feature for let's say a given listing ID L1 over 24 hours window, the feature service dynamically scans through the Bigtable rows, fetches the rows which basically contained within the lookup time and then aggregates the time series values to return the final feature value. So now let's look at the other kind of aggregated real-time feature, which is time series. So in addition to the general listing popularity feature, we may also want to understand the interest of the user who submitted the query, such as the 50 most recent listing IDs viewed by a user. How do we compute that? So from the same view listing beacon, we will now filter all the records that contain both listing IDs and user ID fields. Then for time series features, we don't need to pre-aggregate values. Instead, we'll store each point in the big table with its raw timestamp. Since we set a truncation rule at the request time to return only the most recent 50 listing IDs, the feature service platform basically will perform a streaming scan on all the rows for the feature and for that specified entity ID, the listing ID, and then it retrieves the values until either all the relevant rows have been collected or the listing ID count reaches 50. So with that, let's look into how heaps work today. So heap features at Etsy are a special type of features usually used to determine popular or trending items. It is generally calculated based on the richer count feature that tracks the additional information like the listing ID in this case. It gets stored in a heap store with a special key format designed to ensure the correct ordering during the feature retrieval. Let's take the top purchased listing ID in the past 4 hours. So here you see the pipeline first calculates the purchase count for each listing ID within the past 4 hours, like any other count feature, and then return the count value along with the listing ID as additional context for the heap entry computation. The pipeline then constructs the big table key for the new count value with the feature name, version, heap key, and encoded count string and the item ID. In this example, the heap key is the reserved word all, since we want to compute the total purchase count across Etsy. The item ID is the listing ID, since the feature asks for the top purchase listing IDs. To make sure higher counts are ranked at the top, we encode each positive number with a 9's complement. So for 10, the 9's complement will be 89, and then prefix the number with a string, which is the length indicator. So this length encoding takes advantage of the lowercase alphabet, so we can support up to 26 digits of numbers. So for 10, since the length is 2, the length encoding will be Y. So before pushing the new heap entries in the big table, we pop the existing ones out, aggregate them, and then modify and then store them back again. Now, during the retrieval, the feature service would return the listing IDs and the purchase counts in decreasing order. Similar to the time series feature, the feature creator can specify the truncation options, for example, up to like 50 listings or so. With that, I'll pass it over to Tian, who talk about the overall Rivulet architecture and the feature workflow.
Thanks, Prachi. Now that we have covered how each type of real-time feature is processed and retrieved, let's zoom out and discuss the overall architecture of Rivulet and how it supports our feature workflow. So Rivulet was built and launched in 2019 as Etsy's first centralized feature store. It was adopted quickly by most of the internal ML teams like ads, recommendations, search, etc. It was built for the cloud environment during Etsy's general migration from data center to cloud. And since the upstream data infra migration plan was not finalized by the time, and there was even no clear ML use case of streaming features, Rivulet was designed with resilience to uncertainties in mind and was only targeting a small volume of online requests from non-ML systems. But however, today, the majority of those requests come from ML model inference, so they're often in large batches of many features. So we're continuously optimizing the system to handle the new challenges. Here is an overview of Rivulet's system architecture. Our ingestion pipeline consumes the source event stream and writes the intermediate values to Bigtable after pre-aggregation. There's a daily snapshot job that dumps the Bigtable rows to a GCS bucket for a time machine to compute training data. A feature service retrieves and aggregates rows from Bigtable to compute the final feature values for the online services. When features with like a longer aggregation window, like 30 days or more, are created, we really need to backfill the data from historical events to generate accurate feature values sooner. The backfill job reads from the GCS copy of the event data, computes intermediate representation, and adds to both the production Bigtable and the corresponding GCS snapshots. The feature definition are referenced to determine the computation logics in all of those ingestion pipeline, backfill jobs, feature service, and time machine components. Supported by Rivulet, our feature workflow usually starts with researchers exploring existing features and raw event data. When a promising feature is identified, they define it in the dev environment, backfill for training data generation. And after it's proven to be effective in offline experimentations, we move the feature to production and load the backfill data into the production Bigtable for serving. Feature exploration is really done with either like spot checking using our hydrology tool or value analysis using the BigQuery on raw event data. The hydrology tool calls the ASCII Web API under the hood to translate the listing IDs to listing images for convenience to our researchers and data scientists. For feature registration, like all the Rivulet features are defined declaratively in Scala code, as shown on the left of this slide. It requires some specialized knowledge to engage with, so to make feature creation easier, we have started initial prototyping work with a YAML-based feature registry, whose configs are text-based and easier for feature producers to interact with. Just a note that it is still under active design discussion, so the schema is not final yet. Like in this very initial draft version, we have removed the event filtering logics for upstream applications to handle. When a new feature with a larger aggregation window gets introduced, like I mentioned, we run the backfill job to fill the missing range. With the feature of the listing view count for the past 30 days as example, if we create the feature on October 12th at 9 a.m. UTC, and we plan to start serving this feature in 3 days like today's morning, none of the feature data would have the full 30-day view of historical events. And thus we need to backfill the rows between September 15 and October 12. Oh, sorry. For either an experimental model or production model, training data can be collected in 2 ways. The first one is by logging the production request, which is highlighted in yellow color in the diagram. It is preferred for models that are updated very often and cannot wait more than 1 day for training data. The other approach is by running the batch job that computes the feature values with the Bigtable snapshots. The second approach can generate training data, include the new feature values for requests even before the new feature has been productionized. So ML teams can get any time range of training data as soon as the feature is created. Regarding feature service, the current feature service is built with a simple REST-like framework. The 2 most important APIs are like single feature GET request and batch feature post request. A single GET request requires a feature name, version, entity ID as the feature key. It will return a JSON object with the feature name, version, key, and feature value in it. Feature consumers can also add additional truncation rules or accumulator customizations in the request. The truncation options are like limit the max number of results to return or restrict the time range to slice time source rows from Bigtable. Accumulators provide like additional post-processing options on the results. For example, we may want to get the deduplicated list of buyers' recently viewed listings to help them continue a shopping journey that they might not have finished yet. Or in some other cases, we could make recommendations based on buyers' viewed listings only in their most recent visit session to help them find a desired item more efficiently. Like if we implement all those logics in feature consumer's own client, since the Riverlight feature service communicate with Bigtable through a fixed bound scan query, it may overfetch more results that they need to, or make multiple round trips to sequentially obtain the desired number of unique records. In this demonstrated example, it first fetches the most recent 5 records, does deduplication in its own client, sends another request to fetch the remaining 1 listing ID. But with the dedupe accumulator, we can perform a streaming scan following the observer pattern. So streaming scan has a predetermined start, and Bigtable will stream the rows back to feature service one by one for consumption. This dedupe accumulator only accumulates records that it has not seen before and will return the values once it reaches a terminating condition. And in this case, the terminating condition would be 5 unique listing IDs have been found. The accumulators are like essentially useful to avoid unnecessary requests and data transmitted, and thus further reduce end-to-end latency. The batch post request asks for similar information as a GET request, but allows sending a list of feature requests together. Okay. Despite all the successes, like any other system, Rivulet faces challenges, and we're actively working on optimizing the system using the knowledge we have collected over the years. So for example, like I mentioned, feature creation via Scala code can be cumbersome for feature producers. So we're developing a more user-friendly solution with a text-based feature registry, plus some automatic validation deployment to smooth the process. We also aim to improve the API performance to better handle the growing volume of batch requests. Finally, like the redesign of the system can reduce the complexity of the legacy code and further reduce the team's maintenance burden going forward. That concludes our presentation, and thank you all for your time. And special thanks to our amazing team for their contributions. We're now do we still have
Thanks,
a few
Jenna.
minutes
Thanks,
for
Prachi.
questions?
We're actually out of time. We're going to do a break. I think this is fascinating stuff. I just one quick question, but before we go on the break, I mean, it showed on your pipeline with the feature service that you were passing out the 5 recent activities. Are you using them just to power the website, just to show you're using this whole feature engineering, streaming feature engineering infrastructure to power recent activity as well? Or is that input to a model as well?
Like it depends on the use cases. For some very simple like use case like SE Web API call, it may just directly make the call to fetch the most recent like view listings. But some other models could use those features in their as the like input for the model inference.
Okay.
Yeah.
Great. So we're going to take a break. Thank you. I hope you'll answer any questions on Slack if you jump over there. If there's any questions for you. Fascinating. Great to see you building real-time AI. I think it's the most challenging problem in data for AI that we have today. We're going to be back in 10 minutes or a little bit less now, I think 6 minutes. And come back. We're going to have Strike, Chalk, and others in the next session. You don't want to miss it. See you all in a couple of minutes. I'm going to grab a Right, we're coming back. Kao, am I pronouncing it right, Kao? I guess I'm not.
That's close. Kaio.
Kao, sorry. Kao Kamada. And we've David here as well. Great to have you here. Delighted to have Striker. I think it's your first time talking here at the event. I can introduce our speakers. We have Kao Kamada. He's a software engineer in Stripe's machine learning infrastructure team. The past 2 years, he's been developing Shepherd, Stripe's next generation ML feature computation platform. And Divya Malahar is a software engineer based out of Seattle, working on developing Shepherd, Stripe's next generation ML feature computation platform. And prior to her ML infrastructure work, she spent 2 years working in Airflow. We'll go ahead with usual, try and share your screen, and it's over to you if we can get that going.
Great. Thanks for the introduction. Can everyone
Looks
see
good.
that?
Yeah, we're good.
Perfect. So we'll be presenting about Shepherd, Stripe's new feature engineering platform. We'll cover topics related to the online and streaming portion of our architecture, explore how we've leveraged the open source Chronon project, and discuss the control plane that we created to accelerate feature development. Before diving into Shepherd, let's first talk about Stripe and our use of ML. Stripe is a financial infrastructure company that processes over $1 trillion in payment volume every year. At this scale, leveraging ML across our product line is crucial. As you can imagine, one of the main use cases for ML is preventing payments and merchant fraud. Our models cover not only traditional credit card transactions, but also a variety of other payment methods, including those specific to certain countries. Given our scale, models must operate under strict latency and freshness constraints. Detecting and responding to fraud in real time is essential to protecting our users and maintaining the integrity of our financial ecosystem. To satisfy Stripe's growing needs for machine learning, we decided to build a new ML platform in 2022. Given the adversarial nature of the fraud space, this platform needed to enable quick feature iteration, backfill of historical data, and fast deployments. It also had to support batch features and streaming features with low latency and freshness, both in the order of milliseconds. After considering a number of alternatives, we decided to partner with Airbnb, who also presented at this conference, to adopt Chronon and modify it so that it could work with Stripe's databases and infrastructure. Together, we open sourced Chronon earlier this year, and we're now co-maintainers of the project. The first thing I'd like to walk you through is a simplified example of how a feature is defined in Shepherd using the Chronon API. We'll build upon this example for the rest of the presentation to demonstrate how our streaming infrastructure operates and how data flows through the system. So the feature we'll be creating is a simple streaming feature that you might encounter in a payment fraud model. It corresponds to the amount of money charged on a credit card over the last day. The first step is to define our source. Because Shepherd uses a Lambda architecture, as we'll discuss soon, we need both a table and a Kafka topic. From the source, we only really care about two fields, the card ID and the dollar amount. Here you notice I'm using a cast. This cast comes from Spark SQL, which can be used across Chronon and is applied the same way both online and offline, as we'll see in just a moment. And that's it. So now we can use this source to define some aggregations. To define windows and aggregations, we use the group by API. The feature we want to represent is the amount of money charged on a card over the last day. To create this feature, we will key the event stream on card ID, define a sum operation on the amount in dollars over a one-day window. If we wanted to add more card-related features, we could just add more aggregations or more windows to that list. And that's pretty much it. In practice, you would also use the join API, which allows combining multiple group bys and running point in time correct backfills. From here, Shepherd will automatically compile this code into batch Spark jobs and streaming Flink apps and enable the features to be served in low latency. So now let's go over a simplified version of Shepherd's architecture. As I mentioned earlier, we use a Lambda architecture. So we have Flink apps running continuously and Spark jobs running periodically. Both these jobs produce intermediate data and store it in very low latency key value stores. On the online side, a stateful Flink app processes events from Kafka and pre-aggregates the data based on the group by and source definition, similar to the one we just saw. It then writes this data to a memcached-based KV store. The offline side is similar in principle. The Spark jobs process historical data from sources like iceberg tables and write the results to a key value store. Then at serving time, a dedicated service fetches, merges, and finalizes data from both stores, and the feature vector is served to users. In the following slides, we'll delve a little deeper into Flink and the serving side of the system. So if we're running a Flink application to produce streaming data and Spark jobs to produce batch data, how do we ensure consistency across these two platforms? Well, we essentially just aim to run the same Chronon code in both places. The noteworthy part here is that Chronon supports Spark SQL in its feature definitions. So we need to run Spark inside of Flink. We achieve this by directly utilizing Catalyst, Spark's query optimizer. At the core of this functionality is Chronon's Catalyst util class, which extracts the execution plans from Spark and creates transformation functions that can be executed in Flink or anywhere else at low latency. This is a very interesting part of Chronon and Shepherd, but it's pretty complex, so we won't go into too much detail here. But fortunately, Chronon's open source, so if you're really curious, you can just go and check out the repo. Now let's go into a little bit more detail on the streaming system. For this part, I'll compare the default Chronon architecture, which uses Spark streaming, with the tiled Flink architecture that we developed at Stripe and open sourced. So as I said, the default Chronon architecture uses Spark streaming, not Flink. This approach simplifies achieving online-offline consistency because it's all just Spark, and it's sufficient for most organizations. Here, the source of a feature is calculated using the Spark streaming job. If you remember the one we just created, the Spark streaming job would decode the events, extract the card ID and the amount in USD, and then execute any Spark SQL that is included in that definition. Those transformed sources would then be stored in a key value store. Then at serving time, Chronon would fetch all the necessary events to fill that defined window, like the one-day window we created, perform the aggregations defined in the group by, and construct the final feature vector. Again, for most organizations, this architecture works really well. However, you can imagine the limitations at scale. For example, if a corporate credit card sees heavy activity with 10,000 purchases in a day, serving latency would be quite high. Fetching and aggregating many thousands of events every time a model needs features is computationally expensive. So to solve these scaling issues, we adapted Chronon to use a tiled architecture. The core idea here is to move computation from the feature retrieval side to the feature computation side, thus improving time complexity at serving time. The most significant change is that we pre-aggregate the events in Flink and store the intermediate data as fixed length tiles in the KV store. Instead of just evaluating the source, Flink also calculates the aggregations defined in a group by. These tiles are kept in Flink's memory while they're being calculated. And as events arrive, Flink processes the selects and the filters defined in the source and updates the in-memory pre-aggregates based on the group by definition. It also writes out the tiles to the KV store with every event. So for example, in the feature we created earlier, Flink would maintain tiles containing the sum of amounts for each credit card it has seen recently. This way, instead of storing one entry in the KV store for each event that comes into Kafka, we only store at most one tile per period of time. This approach significantly reduces the amount of data that needs to be fetched and aggregated during serving time, thus improving scalability and reducing serving latency. The end-to-end flow here, or feature freshness, is also quite fast despite the additional work. The delta between an event landing in Kafka and data being updated in our KV stores is almost always lower than 100 milliseconds. So to help visualize these two different architectures, let's walk through a real example. Imagine the 6 following events land in Kafka, each with a card ID and an associated amount. In the untiled or default Chronon architecture, Spark would store 6 individual entries in the KV store, similar to what we see here. In contrast, in the tiled architecture, Flink would pre-aggregate the sum of these events and store the intermediate result as a tile. So for example, the 2 card A events before 1 o'clock would become a single sum value. Then when serving features, the fetcher would gather and merge the relevant tiles. So with this tiled approach, we were able to significantly reduce feature retrieval latency. In most cases, feature vectors containing many hundreds of features can be served in single-digit millisecond latency. As I showed in that diagram earlier, feature serving in Shepherd is done through a dedicated service that runs the Chronon fetcher. And to illustrate how this works, let's walk through an example of feature serving. Let's say it's 1:30 a.m. and we want to retrieve features for the group by that we previously defined using card A as key. Because we use a Lambda architecture to serve streaming features, we need to fetch both offline KV store data, and in this example, let's say the batch KV store contains the sum of 200, for example, and the streaming store contains 2 tiles, one containing value 35.99 and one containing value 40. To serve this feature, the fetcher would fetch all this data, merge the amounts, and compute the final feature vector 275.99. And that's essentially how it works. It's kind of a simplified version, but in theory, in practice, it's kind of how it works. There are several optimizations that we implemented on top of this architecture to further improve scalability, such as using multiple tile sizes and leveraging an in-memory cache. If you're interested in learning more about these optimizations, feel free to reach out to us in Slack or via email. And I'll now pass it off to Divya to discuss our control plane and how it's significantly sped up feature development at Stripe. I think you can share your screen, Divya.
Cool, thanks, Kaio. So we've unlocked the ability to serve large features at low latency, which is a critical requirement for our charge path use cases. However, we found that onboarding new use cases onto Shepherd can be a toilsome process that requires numerous manual steps. I'm going to be talking about the Shepherd control plane, which we've built to automate our infrastructure management and accelerate feature development at Stripe. Onboarding new teams to using Shepherd can be a long, toilsome process for the feature computation team. There are many manual actions required, which does not scale well as we expand the number of ML use cases at Stripe. For each new team or business use case using Shepherd, we manually provision a new Flink application to process real-time streaming data for the team's online feature groups, which are another name for group bys, as we saw earlier. This requires setting up all of the Flink app scaffolding, provisioning Zookeeper and S3 resources for the application, ensuring we have enough capacity to process all of the feature groups, and configuring alerting for the new app. Additionally, running all feature groups owned by a team on one Flink application results in issues with noisy neighbors that can bring an entire app down if any feature groups are encountering problems, and degraded feature freshness as ML engineers add new feature groups and the app is unable to handle the additional load. We've ended up having to provision multiple Flink applications for a single use case, which both blocks our users from serving new streaming features and makes it difficult to scale Shepherd as a platform. Some additional steps that are required to onboard teams onto Shepherd include provisioning a new key value store for our Flink applications to write data to, registering the batch dataset for every new feature group that is brought online, and creating a new Shepherd API tier for feature serving isolation, which also requires manual scaling to account for growth in traffic. You can see in this graphic the number of Jira tickets our team has open every day to manually register these batch datasets for new online feature groups. Typically, all of this setup is a 1 to 2 week cross-team effort, during which our users cannot serve their new online features. Managing the scale of this infrastructure also requires ongoing monitoring and tuning from the feature computation team, which again poses a scalability issue for Shepherd. To combat the amount of manual effort necessary by our team to onboard new users, as well as speed up feature development at Stripe, we've built the Shepherd control plane to empower ML engineers to self-service the creation and maintenance of their infrastructure for model training and inference. There are a few major components we built to make Shepherd an easy-to-use self-service platform with automated infrastructure management. First, we need to understand the concept of a storage pool. Each Shepherd use case at Stripe maps to its own storage pool, which is an abstraction we use for managing the use case's infrastructure. Storage pools are attached to feature groups, as we can see here. Each pool contains information such as which feature groups it should manage, the amount of traffic expected to read these features. The pool uses the feature groups configured to determine which batch datasets to register. Additionally, each storage pool will create its own key value store and Shepherd API tier in order to promote feature serving isolation, which is critical for our users, especially for our charge path use cases. We were able to benefit from using Stripe's programmable infrastructure configuration engine, also known as SPICE, for creating our storage pool abstraction and control plane. In our current Shepherd architecture at Stripe, our ML models read from our feature service via an API tier, which calls the Chronon fetcher under the hood. The fetcher reads from our KV store and batch datasets to compute the feature values. All of this infrastructure was previously manually provisioned and managed. The first piece we built as part of the process of onboarding onto Shepherd with the control plane is our custom CLI tooling. With easy-to-run commands, users can create and update their storage pools, which will auto-generate the code for creating and scaling a new Shepherd API tier based on the user's specified expected traffic, adding and removing feature groups from the storage pool, as well as updates to any other pool configurations, and finally managing the deployment ordering for pools and API tiers based on the configured criticality of the pool. This means users can specify a new region on their storage pool via the CLI tooling, and all of the infrastructure will be automatically provisioned in the new region with no manual work from ML infra teams needed. Each storage pool has its own service, which is auto-deployed daily. During these deployments, the Shepherd control plane store for the storage pool, provisioning batch datasets for each online feature group in the pool, and deploying an individual Flink application for each online streaming feature group. The control plane uses temporal workflows and is built to be idempotent, resilient to outages, and manages the scale of all Shepherd infrastructure. Our integration with the Flink control plane has allowed us to automatically provision a Flink app for each individual feature group. Having this isolation results in fewer correlated failures, better feature freshness, and ultimately improved model performance. The Flink control plane manages scaling the application based on heuristics such as the job graph size and configured parallelism, so managing the scale is not an issue for our team anymore. You can hear more details about the Flink control plane and how it was built at Flink Forward next week. Stripe operates as a multi-region company, so high availability and feature freshness are critical for our large use cases. Via the control plane, we are able to automatically enable cross-region replication on the pool's key value store for high availability in case of regional lag, as well as check the scale of the cluster to prevent it from becoming overloaded as we spin up additional Flink apps. The control plane notifies teams of any manual actions that are necessary by automatically provisioning Jira tickets, and also notifies pool owners of any important actions taken by the control plane via Slack. Additionally, we were able to use the storage pool abstraction to create a custom internal UI for tracking pool status changes and metadata. This makes it easy to understand what features are being used by which teams, as well as easy to track the pool deployment progress. We are currently in the process of rolling out the control plane to all of our Shepherd ML workloads at Stripe. The control plane allows ML engineers to rapidly develop new online features without being blocked by the manual scaling and provisioning requirements needed by our team. Additionally, our users are able to benefit from high availability on their Flink applications and improved feature freshness via automatically enabled cross-region replication. This combination of accelerated feature development, reduced toil for the ML infrastructure teams, and improved feature freshness contribute to better model performance and ultimately growth in fraud loss savings for Stripe. We are continuing to develop on the control plane to add automation and safety guardrails where needed, and ultimately make Shepherd an easy-to-use self-service platform for ML engineers at Stripe. Thank you.
Fantastic. Thanks very much, and Divya. I think been quite a lot covered in a short period of time. I'm going to ask a quick question about storage pools. I think it's interesting. Are you actually, is this a kind of a data mesh style architecture where business units take responsibility for their services? You know, that they're almost like microservices. Okay, you got this team gets this one and this team gets this one. Is that the goal, to have that and not a centralized team responsible for infrastructure?
So that's a good question. Our ML infrastructure team is responsible for maintaining and like deploying all of these storage pools. So we separate it on like a business use case, but ultimately the pool owners and the business use case teams don't need to manage deploying Flink applications. They don't worry about any of the infrastructure, but all they need to do is update the feature groups on their storage pools. But ultimately, our team is responsible for managing the pools
Fascinating.
themselves.
I think if you more questions are out of time, you can jump over onto Slack. We can take them there. I think there's one in the chat. You can take that one in the chat as well. And with that, we're going to move on. Delighted to have Chalk here for the first time. Chalk are a new vendor in the feature store space. They are going to talk about real-time feature serving for online inference. And we're delighted to be joined by Elliot Mark. So Elliot is one of the co-founders of Chalk. He started his career at a firm where he built the early risk and credit data infrastructure. That was the inspiration for Chalk. And he then co-founded Haven Money, which Credit Karma acquired to power its banking products. And he holds a BS and MS in computer science from Stanford. Welcome, Elliot. And let's do the formalities of trying to share your screen. Let's see if it works.
Great. Yeah, thanks so much for having me. I think the host has stopped my video, so I can't start it. But oh, there we go. Thank you so much. Yeah, so here to talk to you today about Chalk. We started this company about 3 years ago, and serve today about 25% of all card transactions or debit card transactions in the US. A bunch of other fintech applications, also some really cool things in e-commerce and healthcare. And I'm going to talk to you today about how you can build your feature platform with Chalk. I think a lot of what you might be thinking about when you think of a feature store is like a database that you write to. But what we're going to do is connect you to where your data actually lives and be able to process it in real time. So what we're going to look at today is an example of a fraud application. So we're going to have transactions and users and credit reports and things like that, and try to figure out who the good users are and who the fraudsters are. So what's on the screen right now is a set of features for transactions. We've got simple scalars like IDs, amounts, memos, and that kind of thing. You'll notice it's all very Pythonic. Like you just put a little decorator on top of a class called features. And then you can define the features you want and put the comments in your Python. And we'll treat this as a kind of a DSL and get it syndicated to the web and any of your generated API clients. You can also have relationships to other bags of features. So instead of having kind of like flat tables, we want to model the richness in your data and say, well, you know, I have transactions, they have users, users kind of have credit reports and many transactions that link back to them. They have trade lines on credit reports. So we want you to model all of the richness in that data and try to keep this as Pythonic as possible. So once you've kind of modeled this data, you can also write features in really terse syntax to say things like, show me the count of purchases where the category is food and drink, and you know it's from this time, and give me the count there. So we haven't done anything though to connect this to data. And so after we've written our features, we need to go hook it up to where the data lives. So we can do that. I'll show you kind of two ways. One way is by SQL, and another is by writing Python functions. So with SQL, we can just write a plain old SQL file. Like if I run this, we see some transactions coming back here. And we can say that it maps into a feature class, in this case, transaction, by way of the names of the columns that are getting returned. So here we've got returned column names like ID, amount, user ID, @ and memo, all of which line up with properties of the transaction. So what will happen is that at runtime, we're actually going to go talk to your Postgres database to go get this data out. We can do the kind of like reverse ETL thing too, but often managing all of that state becomes a real headache. And even at real scale, you can often just get the data from the source of truth. Now, pulling all of your transactions would, of course, be way too much and really slow down your application. So what we do at runtime is insert filters on here. So if you were asking for the transactions like for user ID 1, we would push down a filter or push down aggregations and projections into this query so you only get back the rows that make sense. Now, you can also write Python functions on top of this same DSL. So for example, as a really simple one, I could want to write a function that compares someone's name to their email. This is a great fraud signal. I just kind of want to know, like, does your name sound anything like your email? So I can pass in, I can say I require someone's name through the type signature of my Python function. So I need a variable called user.name or with the type user.name, and I need an email with the type user.email. And I'm going to compute the Jacquard similarity by saying, give me the length of the intersection of the characters in the name and email divided by the length of the union of those same characters. And that'll get me this name match score on my user class. So once we've written a couple of these features, we can go try something out. So we can say, hey, okay, that name match score feature, what's the value of that particular feature? And I can get that back. But I could also ask back for a little more data. So I could say, for example, well, you know what, show me all of the features of user. Or if we wanted to get a little crazier, I could say, give me actually a lot of stuff. I want to know, like, what does the user look like? What are the trade lines for the user? What are all of the transactions for the user? And what we're going to do to compute that is build a query plan. So there's no kind of concept of like a feature view or like a singular set of features I must be querying or something I must set up. Much like when you query your database and you say, here are the columns I want, here are the features I want. So too will we plan this query at the time that you need to go grab the data. So for this really complicated one here, this is what that query plan looks like. But if we jump back to one we ran to before that, this is quite simple. And so we'll start here. Basically, what we needed to do to compute someone's name match score was we passed in user ID. So we needed to figure out what was that person's email, and then we needed to feed it through our Python function for computing that name match. So that's kind of what's going on with Chalk. So ultra low latencies if you want, including around the 5 millisecond range. But we can also process really complex queries and queries that need to process a lot of data. Now, the next thing I want to show you is that it's really easy to iterate on this and to come up with new features. So what we might want to do is compute a new feature, for example, for someone's fraud score. So what I'll do is I'll say, I want to make a new feature that says get fraud score. And I'm going to base it on some of the other features that we've written before. So what I'll do is I'll take in someone's, this name match score that we wrote up here. So let's take that one in. I'll take in whether or not someone was deny listed. So user.deny listed, and we can, see where this is used here. Someone is in a deny list if their email, appears in our deny list, which we load up from S3 in this case. And I could take in, I don't know, maybe how old their email is. So here's this email age days feature. The way we kind of compute this is that we work with a vendor called email age. And email age, given an email, can give us a big body of response that's going to be this email age response. And kind of downstream of that, we could say we know how to take someone's email age response and parse out some of the meaningful features from it. So this is kind of the idea behind Chalk. You're not explicitly linking any of these steps together. You're not saying like, please run this function, and then once you've done it, run this other function. You're saying these are some kind of providers of functions that could be used as part of a computation graph to go get an answer. So this is going to pull out that email age days feature, and we're going to use that in our new fraud score. So we'll say, we're going to decide that if you're deny listed, that means your fraud score is 1. Otherwise, sure, we'll try this. It's going to be the average of your name match score and your email age days. So I'll go put this feature on my user here. And what we'll do is go query for this feature value. So to do that, I'll hop over to the terminal here, and I'll deploy my change to a branch. So this is going to pick up my Git branch. In this case, my Git branch is called main. And all of that code will be running in my cloud. So I can go talk to production data stores. I can go pull out real data and see kind of what's coming back. Also, I can run all of this locally if I like. And I can run these queries against this branch to see what that fraud score would be. Now, we can see this new feature coming back, user.fraudscore of 259, which is going to be the average of my email age days and my name match. So we could go iterate on this a little bit. And we can do this even like just by watching our code. So I could say, for example, that I want to watch my local changes. And anytime we make a code change over here, we'll run a deployment and rerun that query so that we can see what the value would be. So just stretching this out a little tiny bit, let's iterate on this and say, well, if my name match score is greater than 0.5, that's pretty good. Otherwise, if my email age days is low, the kind of default here is going to be 0. So I'll go save this change here. This will get picked up for the deployment. And then we'll see this new feature value come back. And now my fraud score has gone down to 0. So this makes it really powerful to be able to try things out like this. Like you can just kind of dream up an idea, code it, and query it either online, or you can run a big backfill. And what's really cool is that all of the same features can be backplayed because we're tracking when they're occurring. There's a concept in Chalk called a feature time. And the way this works is that if we return a feature time from any of our resolvers for any of our features, in this case for transactions, we're returning this @ column that we're tracking in our Postgres database for when a transaction happened. We can then go back in time and ask what would the transaction have looked like at a given past point in time. So that lets us try out this fraud score in a backfill scenario and to say what would happen if. These also execute extraordinarily fast. So even in these cases, for simple Python functions like this, we'll take this Python function and completely understand its AST and run this as an expression. So it's kind of an unfair advantage against Python, where we're kind of running this in just C++ as opposed to needing to go, grab the GIL and run these Python functions directly. So that's a little bit on what it looks like to iterate on some feature sets and come up with some new values. We can see what this also looks like in the web here. So every time we're running these queries, we're going to get back a link to the how these query plans looked. And under the hood, we're doing a lot of things. If you've ever looked at like Postgres explain analyze or Snowflake's query plan viewer to do things like merge joins and distincts and projections. There's also a lot of caching built in here. So I think sometimes when you think about feature store, you really want to know, can I like load up my feature store and can I unload from my feature store to query it? And one great example of that comes via expensive API vendors. So for example, let's say that I wanted to kind of clean up my transaction memos. And instead of using a provider for this, like a Spade, I actually want to use OpenAI or use Gemini to figure out, like, is this an ACH transaction? Is it a non-sufficient funds transaction? What's the category or the cleaned up memo? And so I can do that by also writing one of these Python functions. So I can say, given a transaction memo, I'm going to compute the transaction completion by asking my model, in this case, Gemini, what is the category? Is it NSF? What's the clean memo for this given transaction memo? Now, downstream of that, again, kind of taking this result type, I can say, well, given this completion, I know how to load that up as JSON and extract these fields here. But this completion is actually really expensive to compute. So I'm going to say that I want to that I'll tolerate a maximum staleness, we call it, of infinity. And this means that if I've ever computed this value for the transaction before, I don't want to recompute it. I just want to sample it from that online store. And so you can do the same thing too if you have like a bunch of data in Snowflake and you want to go put it in the online store on some cadence. You can kind of make those queries to pull back that data on a schedule, load it up, and have it available at runtime. So you really get the best of both worlds, where you can go compute stuff on the fly, really any arbitrary Python at all, including calling out to APIs like Gemini or to vendors like EmailAge if I wanted to go ask them for some data, or if I wanted to kind of even do it across these relationships. So if I wanted to say, given a username and a date of birth, I know how to go fetch the user's raw credit report and the user's ID. And then from the credit report, I know how to fetch someone's trade lines from the credit report, for example. But being able to model all of these relationships without having to confine yourself to like a fixed table allows you to kind of express things really naturally, like in the way that you would think about them as you're just trying to write like a little toy Python program, but with the kind of performance and scalability of a real production tool. I just briefly also want to touch on the fact that we've got all the normal like feature discovery and cataloging things here, so you can figure out like what features are being computed, how they're being computed, on kind of what latencies, in which named queries. You can set up all kinds of alerts and monitors and things like that, and you can do all of that from the code. Finally, all this just runs in your cloud. Almost everyone we work with has very stringent compliance requirements, and so we deploy to all the 3 major clouds. I think that's about my time. I'd love to turn it over for any questions.
Thanks a million, Elliot. I just put on my video here. There was one question. We'll just take that question from the Q&A. How is the scalability of Chalk? Maybe I can add a little bit to that. I mean, you talked about some of the Python functions. Ones are using models, and if you're going to use a Python library. So how do you handle all the complexity? I guess you're going to have a mix of different backends, right?
Yeah, absolutely. So from a scalability perspective, we're serving this for at kind of a very, very high QPS for a lot of different customers. One example is Whatnot, for example, the e-commerce platform. They're the largest live streaming platform in the US, and they are doing this to rank all of the shows on their platform, so that when you kind of show up and you want to start sorting through things, you want to like pick the sneaker show or the card show or the Pokemon cards show. And so what we do for them is that we have some mixture of these different types of features. So our kind of approach is like try to compute everything you can on the fly, because that's the simplest mental model, and we'll do everything we can to make it efficient. So if you do need to run Python, we can't figure out how to transform this AST into a C++ expression, we'll run it on many different Python interpreters kind of sitting behind the query server, so that you're actually not GIL-bound for those functions. If you're going to go talk to like a DynamoDB or a Postgres, like we're going to use the native drivers to talk to those. So we use the C++ client to go talk to Dynamo. We use libpq to go talk to Postgres, for example, to try to get you as close to the minimal latency on using any of those data stores. I think sometimes people think like, oh, I can't, because this is a big application, like I can't serve real-time features, or I can't go compute this on the fly. And we've often found like you'd be surprised at how much you really can. Like 20 milliseconds is a huge amount of time, and it's plenty to go talk to Postgres and run some Python functions. If you're in the realm of needing responses, under the 10 ms framework, then maybe you can run like 1 or 2 Python functions and like mostly some cached values. And if you happen to have like a whole second, well, then you can kind of do anything. So we try to just work with our customers on what works for them.
Airbnb talked earlier about shifting left, so pre-computing as much as possible, but you're arguing for shifting right, effectively pre-computing as much.
Yeah. I think the thing about pre-computing stuff is that you're going to miss some real-time data. If you've pre-computed something, we have a lot of customers who do card fraud, for example. Card fraud happens in seconds. It doesn't happen in hours or days.
Yes.
We'll do the kind of materialization stuff if you want to kind of partially pre-compute some things, and sometimes that can be a good trade-off. For our like very largest kind of Fortune 500 banks, that's something that we do and is really successful. But I think that having that state kind of float around can make things really complicated. And so if you're able to shift that to the time of compute, it's going to be very fresh.
One last question before we get into the next talk. It's actually a segue into the next talk, because you were talking about data modeling. So feature stores kind of started with key value stores, and with key value stores, we don't have typically that relational data model where we can have foreign keys and we can have different data models. And we've seen most feature stores have gone with star schema. But so the one issue about going beyond star schema to maybe a normalized data model or a Snowflake schema data model is that what's your backing stores? Do you map it onto key value stores, and then the efficiency of you get a lot of round trips to the key value stores? Or do you prefer, if you have a normalized data model, to map it to a different online store, a relational data store?
Yeah, thank you. So this is what's so cool. We're building a query planner. So our code looks very similar to how Postgres looks, to how Snowflake looks. And the reason that when you build a feature store, it's easier to start without doing that is because building a database engine is really complex and really tricky. And certainly our first couple attempts at this were not query planners. But if you can do that, then you can delegate to these stores really efficiently. So we still do map this, and we'll use DynamoDB or Redis or Elasticache or Postgres as our online store, kind of whatever you have in the cloud. Our goal is really not to introduce new technology into your
But do you have a preferred mapping? Because if you have obviously nested tables, then there will be there's an impedance mismatch with certain classes of store.
Yeah, so we work really hard on the schema for what each store provides. So in Redis, for example, H sets are definitely the most efficient way to do things. And in Dynamo, it's actually better to kind of have extremely wide tables. So and all of our connectors are written in C++ or in Rust. So we're talking to these stores, kind of as fast as you can imagine, and we're bringing these latencies down to the kind of 5 millisecond regime by way of using the very.
I think we're out of time, Elliot. But thanks. It's been brilliant, very educational, and hope to hear more from you in the future.
Thanks.
So with that, we're going to move on to Javier Del Rue Martinez from HopsWorks, my colleague. And like I mentioned, he's going to talk about data modeling in feature stores. So the journey from going from star schemas to Snowflake schema data model. Javier is a research engineer at HopsWorks, where he's actively contributes to advancing the HopsWorks feature store platform. He's currently pursuing an industrial PhD at KTH in parallel. And he was also the first author on the first real feature store paper at a leading database conference at SIGMOD in 2024. Welcome, Javier. Can you share your screen? We can get started.
Yes. Can you see it?
Yeah, looking good.
Yeah. All right. All right. Thank you very much, Jim, for the introduction. I'm very excited to be here. It's the first year that I joined the Feature Store Summit as a speaker. And in this session, I will talk about Snowflake schema, data model, and what it brings to feature stocking. We'll be talking a little bit about dimensionality and dimensional models, and also normalization. And I will be focusing more on the online store and real-time use cases, and what are the main benefits that Snowflake schema data model can bring to the feature store. So just as a quick recap from the previous talk from my colleague Ray, Feature Store extends the lakehouse to become an AI lakehouse. Basically, the offline store as an open lakehouse is complemented with an online store and a vector index. As you know, offline stores are commonly based on or built on columnar store. So they are more efficient or performant for historical data and contextual information, and also for time series, and they support better complex analytical queries, specifically temporal queries. And then for the online store, they are mostly built on top of row-oriented stores that provides low latency vector retrieval and real-time transformations, which are more focused on real-time cases. And as well, we have the vector index for providing similarity search on vector embeddings. So if we have a look at a common non-real-time AI lakehouse, one of the patterns that we often find is the following. We have an event pass receiving events, business events in this case, and they are consumed and transformed, and they are together with business information from operational databases combined and written to the offline store. And then from that, this data will be synchronized to the online store and the vector index. So if we look at this diagram from a data modeling perspective, we can think of business events as facts in this case, or measurements. And then the business information is basically what we can call dimensions or attributes of these measurements. And then on the offline store, normally data is organized following a dimensional data model. We see that most feature stores support star schemas, but they not many support, or it's mostly a star schema, but not a Snowflake schema. So regarding the star schema, the degree of normalization is a bit lower. Duplicated columns are allowed on the dimension tables. So there might be a little bit more of redundancy in some dimension tables. So these duplicated features. This schema is good for offline stores in the sense that since the query engines are not optimized for joins, there is no need for using nested left joins. So the star schema works fine for these cases. And then on the other hand, if we look at the online stores, we see that online stores are primarily using key value stores, and this is because of the primary key lookups. And basically, they can accommodate the star schema, but key value stores can show limitations in terms of support for joins or more complex joins, and of course nested joins, and also they normally don't provide relational support for relational data models. So in the case of the search schema, for example, they can accommodate it by running iteratively primary key lookups on the dimension tables and then joining the data together. So here, at this point, what we can think of, what we can ask ourselves is the key value store actually the best option we have for an online store? And also, can we actually benefit from using a Snowflake schemas on the online store, and if we have support for relational data models? So to answer this question, basically, the first thing we need to see is to think what could be the best data model for a feature store. So we can have a look first as OBT schemas as a first alternative, or one big table in which we have all the features and labels together in the same table. And this can work on the offline store, since we have columnar compression, and also this might work better for complex analytical queries. But when it comes to online stores when it comes to online stores that are row-based, there is no columnar compression, so data will explode, and it's not really working in this case. So another alternative would be the star schema, as I mentioned before. It works a little bit better. It provides more normalization. So we will reduce redundancy in the features, and also it can work with the online store doing these iterative primary key lookups that I mentioned before. But still, we might see some redundancy in the features, duplicated features in the different dimension tables, and especially, which is what I wanted to focus today, in online cases. Using a star schema brings some new challenges, like the availability of serving keys in the online inference pipeline, which is something that we will see in the following slides. So another alternative in this case is the Snowflake schema. There is a little bit more normalization, so we reduce the redundancy of the features. So they are basically, we improve discoverability of the features and reuse of these features, and it's related to when it comes to the online inference pipelines and the serving keys that I will mention before. The Snowflake schema can basically improve the way applications enrich the requests enrich the request with contextual information. So let's have a look at an example using credit card fraud detection use case. So related to business information, we have credit card transactions. We might have the concept of fraudulent transaction, and also we will compute some aggregates on the recent activity of the credit card. And also, yeah, we will have some details about the bank accounts and the banks themselves and the merchant. So the first step here is to define the prediction problem, whether a credit card transaction is fraud or not. So in this case, we will define our label. We will identify our label and define the label feature group, which is, it would be the fact table in this case. So in this case, we will pick the credit card transactions. Then with the rest of the business information, we define the dimension tables in terms of like grouping them together if they make sense semantically, like features that relate to bank accounts together and so on. So after doing that, if we take into account the star schema, if we decide to organize our tables following a star schema data model, we will have the transactions table in the middle, and then we will have foreign keys or surrogate keys pointing to these dimension tables. Then when it comes to online inference pipelines, things get a little bit trickier. So in the ideal world, if we have an application that tries to detect if a transaction is fraud or not, when the transaction is being processed, the application will use a transaction ID and try to retrieve related information to the bank details and recent activity of the credit card and so on. But in the real world, the transaction has not happened yet. So this transaction is not available at prediction time. So therefore, you cannot retrieve the value using just the transaction ID. In this case, the application would need all the foreign keys to retrieve the corresponding data to enrich the request and before passing it to the model. So this is the first problem. One alternative to fix this problem would be if we decide to create a mapping table, for example, that basically maps the transaction ID with the foreign keys, and then the application could use the transaction ID to get the rest of the keys, and then you can retrieve the corresponding data from the dimension tables. But then the second problem appears, which is you will have to handle or maintain additional ETL jobs to basically keep this mapping table up to date. So it's not really a solution. And then another approach would be if you decide to denormalize the credit card transaction table, the one with recent activity with the aggregations. If you decide to duplicate some of the features from the other dimension tables and added them to this table, then the application can basically retrieve all the features at once using the credit card number in this case. But the problem here again is first you have duplicated columns, and then also it means that you will need still to use additional ETL jobs to maintain the denormalized tables. So you have to update the features in all the places that you're using it. So what about the Snowflake schema data model? If we decide to organize our data following this schema, again, we will have the transactions table as the fact table, and then we will have a foreign key to the merchant's details, and then a foreign key to the aggregates or recent information, recent activity of the credit card that contains foreign key to bank details and another foreign key to the bank account details. So in this case, if we look,
that's okay, but we may be a little
sorry, okay, I will continue. So in this case, we look again at the online inference pipeline. Is it all fine?
You can continue, Javier.
Okay. Yeah. So in this case, we again see at the have a look at the online inference pipeline. We see that the application just needs to know the credit card number and also the merchant ID. The application does not need to to know the bank ID or the account ID. So in this case, we basically are reducing the number of serving keys that the application needs to know at prediction time, and also no additional ETL jobs are needed to maintain duplicated features or additional dimension tables. So now, how we support Snowflake schema data model in HopsWorks. Basically, in HopsWorks, we use RunDB as our online store. RunDB is a in-memory distributed key-value store with SQL capabilities, so it supports relational data models, and also there are some optimizations when it comes to projection pushdown and pushdown of left joins, and also left nested joins. We have some peer review results that we published in our research paper at SIGMOD this year, where we have some numbers here. So we compare how push down left joins perform compared to iterative primary key lookups, and also comparison between star schema data model and Snowflake schema data model. And we saw that basically for the star schema, we can reach a reduction of 30 to 50% in latencies, and also an increase between 50 to 200 in throughput. And when it comes to the Snowflake schema, the reduction is a little bit less, it's 20 to 40 compared to the 30 to 50 for the star schema. And for the throughput is more or less the same. So the point here is that if you use a star schema or the Snowflake schema, they show comparable results, and they basically perform much better than if you do iterative primary key lookups. Yeah, so if you have, if you want to dig a little bit deeper on the experiments or how they were performed and explanation of the push down left join, so feel free to get access to the research paper. And also another benchmark that we did was related to feature vector retrieval, where we compared the performance between another two cloud feature stores. And basically we compared the feature retrieval with different batch sizes. And for example, using batch size 1, a single vector lookup, we see that for P99, we reached between 15% to 11% less latencies. So this is the last slide, I think. So when it comes to data modeling using the HopsWorks, data modeling in HopsWorks, you can use the Python API that we provide different classes for the different abstractions like feature groups, feature views, and so on. So you can get the different feature groups. And if you see on the left, this is the way you could create the query, the nested join for the Snowflake schema. So you basically, starting from the label, which is will be the left most feature group, you start selecting the features and joining them with the other tables. And the HopsWorks optimizer will know which are the primary keys and foreign keys to do the joins. And then on the right side, you can see how the star schema could be implemented. Then you can create a feature view, basically calling the create feature view method and passing the query, specifying which is the label. And then when it comes to retrieving feature vectors in the online inference pipeline, as you see on the left hand side, you need to provide less serving API keys because you're using the Snowflake schema, and on the right side, you can see that you need to provide the bank ID and the merchant ID as well. So this is all for today. I hope you find it interesting, and also if you have any doubts related to the implementations or benchmarks, feel free to have a look at the research paper. Also, there is the feature store benchmarks that are open source and public. And also the last thing, the star schema and Snowflake schema data models are also explained in the book that Jim Dowling is writing. So thank you for listening.
Thanks, Javier. I think we're out of time for questions, but if you have more questions, maybe you want to ask about, for example, about the offline store, how Hopsworks does push down left joins in the offline store, jump over to Slack and do that. We'll move on to Intuit. So glad to have Intuit here. I think Vijay is online. And I'm not sure if Harish is online. Vijay, are you there?
Yeah, I'm here. Both are here.
Okay, so and Harish is here as well.
Yes.
Great. Okay, you're both here. So let's get started. So you're going to talk about feature store as a service at Intuit. Harish Nagusana is a software engineer on the feature management platform at Intuit, where he contributes to the creation of a scalable AI platform that accelerates innovation, empowering Intuit's data ML engineers and data scientists to build data-driven applications that deliver business impact. And Vijay is an engineering manager in Intuit's core AI platform group, where he leads several AI platforms capabilities, including the feature management platform. Do you want to try and share your screen, guys, and see if we can get this party started?
Thanks, Jim. Thanks for the introduction. Going to slideshow mode.
We're looking good. Over to you.
Hi, everybody. So my name is Vijay, and I have with me Harish here. I'm the engineering manager at Intuit, and Harish is a staff software engineer. We are in the core AI platform at Intuit. And thanks, Jim, also giving us a wonderful introduction. So today we are going to talk about our feature management platform and how we have supercharged Intuit ML developers in accelerating their model development lifecycle. So it's a quick introduction to model development. I'm sure pretty much everybody is aware of it, but just want to base ourselves here. So a typical ML MDLC includes several phases, and I'm sure everybody is aware that the most critical or most time-consuming phase is the creating features, for which they start from the users of the system or MLEs or data scientists or anyone trying to deploy a model in production at scale. Right, so they start with data exploration and then creating features, which includes transforming the source data into the feature required by the model, creating, training, and deploying the model. And this is an iterative process and repeated until the goal of the model is achieved. Going a little bit deeper into the feature, creating feature aspect itself. So what we've provided as part of our feature management platform, the architecture is as follows, right? So the user of the system, as I explained, is the MLEs or data scientists or anyone developing models. They start with the data exploration, which could be real-time data coming through Kafka topics, or a batch data, which would be available in our data lake systems, storage systems. After data exploration, they go into feature engineering phase, where they could be simple data pipelines or complex logic that is transforming source data into features as needed by the model. To provide simplicity and uniformity in terms of how features are ingested into the platform, we provided this architecture where features are published to Kafka topics, and from then on, our platform will provision the necessary infrastructure required to read those, consume those features and persist in our online and offline stores. Once the features are persisted in our stores, we provide mechanisms to access those features. For offline store, features can be accessed that can be used for exploration and training. And for online store, the features can be accessed through our online serving layer, which is a real-time API layer, which will make the features available in real time for model inference. So as you can see, like feature engineering itself is a complex workflow, but on top of that, the user needs to think about
a lot of these other things, like, registering the schema properties, discovering features or existing features that they could reuse, figuring out the read permissions and write permissions for a feature, how do they scale and monitor their feature engineering pipelines, stuff like that. So this is where, we try to streamline this, and this would take a lot of time for our users in the development flow. And this is where, we try to streamline our feature management lifecycle. And we have 4 stages here. The first stage is the schema registration, where the users will register the feature set schema, provide the names of the feature, the data type, and data classification and stuff like that. Once the feature is registered, they go to the next phase, which is onboarding. Onboarding is where, once the features are registered, onboarding to our platform, which would involve us to provision the necessary infrastructure to take the features and ingest it into our feature stores. Once that is done, then it's immediately available for consumption. So Harish will go into detail of a little bit detail in each of those 4 steps to see how we have enabled it for our customers.
Thanks, Vijay. The users, as Vijay mentions, our typical users are like ML engineers and data scientists. So they land up into AI Workbench, where we serve feature store as a service over there. Using that feature store console, user can interact and then create their features. So AI Workbench is a new dedicated development environment for all the ML to create ML and AI applications within Intuit. So users will land up here, and it's all self-serve. And users register and then onboard and then manage their features, and then they can very well see their onboarding steps, like so how far it has been progressed. And then once onboarding is done, when the pipeline is live running, they can see the live status as well. If the pipeline is running, how much is the traffic is coming, those steps also those metrics also be available in this console. And then users can anytime add or delete the features. They can modify anything over there. And then the deployment, users want to test their features in the pre-production environment, like they want to test end-to-end over there. Once they are confident, and then they can move that particular step into production. And all these will be like users would interact, like these infrastructure will be available in minutes, so that they can very well use this few minutes without any manual intervention. Going on to the steps, like as Vijay mentioned, so there will be typically in feature management lifecycle 4 steps will be there, starting with the schema registration. Users mention their define their schema, like feature sets. What is the name of the feature set? What are all the features available in this feature set? And then what is the data type for that feature set? Once and then we take like some more information. If it is what is the classification? So is it sensitive information? And then CCPA related, like if they want to get the like GDPR results to get the data, delete the data, we take that information as a part of like registration. And once we collected everything, and then when they started registering this feature, our backend services will validate this information. If it's good to go, then we store this metadata in central repository. And after that, like users can anytime add, update, delete the features in this particular feature sets. Once it is available, and these registered feature sets metadata will be available in central repository, and using data catalog service, users can view their feature sets. And the typical users first will see if the existing for their use case, the feature set is the features are available in any of the feature set. If it is available, they can reuse those feature set. This will help us remove the redundancy, and then ease of use, and they don't need to do extra effort on that. And after that, onboarding and infrastructure provisioning. This is the key part of this entire workflow. Once they register the schema, and then they click on onboarding, and our workflows runs to create the infrastructure. The first part of that one would be online or inference table. Like we take the information, like if they want online or offline, both kind of thing. Our online inference table would be on DynamoDB. It's a key value based low latency store, and then we provision that database first. And then we have like an Intuit, the stream processing platform, which is a real-time processing platform, and we provision that pipeline, and which takes the information from the Kafka, reads the information from Kafka, and then update this online inference table. And to retrieve the features, whatever it is stored in the online inference table, this will be exposed to GraphQL service. And so this service is ensuring that effectiveness, like access also, like, so means add here the security rules, like the users only can get the only his data, not the other data. This GraphQL service is like responsible for that one, and then interact this DB. And if the user opted to choose like offline job, like we create that offline job, like, so using the Kafka, and this is the this offline job runs periodically and takes the information like Kafka information, and then create Hive tables on top of S3. And all these will happen like in few minutes, like these workflows, like, and this all these systems will horizontally scales, be it in data pipeline, be it in online table. If the during like tax season, like our systems like needs to be we upscale that system. If the traffic is, if we get like more than the expected one, even our systems are capable to horizontal scale. The pipelines will get added the more and more parts, and then online table would increase in AWS, like the auto scaling will be there. And then ingestion. So all the users will do their feature engineering, and then we provide them like SDK to ingest the data. This SDK will simplify and then make it like a unified way to ingest the data, and it is available both in Java as well as in Python programming language. Their users, that ML engineers and data scientists, can opt the programming language of their choice. Once they are done with the feature engineering using this SDK, they convert the features into a raw format, and then update, ingest their data. And the online, the stream processing pipeline, or like offline job, will process this data, and then make sure that when they put the data into corresponding table, is it offline or online. And then the consumption part, as mentioned earlier, the consumption would be through GraphQL service. When the users, like in the during the onboarding process, like we update the schema of that GraphQL service, like each feature set will have their schema, and then the key what the features needs to be interacted with. And this GraphQL service, again, it's a low latency store, and low latency we serve for typical P99 like 70 milliseconds, and P50 would be like around 30 to 40 milliseconds. We serve that one. And again, this service is like auto scaling. If the traffic is more, like if you get like more and more traffic for model inference online, and then this will get automatically get scaled up. And we have like for particular use cases like caching layer as well, so that it will very well reduce the latency. And this once, like when the users register, these features will be inferred in a model execution service. Like there is another platform and another service within Intuit. It interacts this with a feature store service, this GraphQL service. Users no need to like worry about the permissions or any scaling kind of thing. So once they onboard, like we integrate every schema, every feature into that into this GraphQL in model execution service, so that it will be available in online inference from this service. And these features, like not only users can combine the feature set, like feature set is the key, the main data store, and users can query like multiple features in across the feature set, so that it's easy, and then for them. And offline stores, as I told, it will be on Hive tables on top of S3. We store that one. Users interact like pretty much like anywhere, like typically Athena or Databricks, they interact, and then they train their model, they explore their model, and then using the results, they very well test in the offline store. And I'll hand over to Vijay for we can give you the summary of.
Thanks, Aris. So this is the last slide. So in summary, how we supercharged ML development at Intuit is, the first thing is making it self-service. So users can get started and get onboarded within minutes. And by having onboarding integrated into its AI workbench, it is one-stop shop for all ML development, including feature management. So this tremendously increases productivity, and also the platform promotes feature discoverability and reuse. By providing SDKs, it simplifies data publishing. So there's only simple ways for users to publish data, and they can use the programming language of their choice to publish the data in a consistent manner. We provide both offline and on real-time feature serving, catering to diverse application needs. The platform is highly scalable and ensures low latency feature retrieval. It has auto scaling built in. It also has security and reliability built in, which are integral to the platform's design, safeguarding valuable data and ensuring consistent performance. So I hope this was informational. Please let us know if you have any questions or if you want to learn more about the platform.
That's brilliant. And I think there can be questions on Slack, so jump over to that. But I can ask one or two before we start, or before we finish up for the break. I can start, I guess, with the Java and Python. We haven't seen too many people today, and in general, supporting multiple language level APIs. Is that performance and usability, or it's obviously extra overhead for you to manage multiple APIs?
I think there's it depends on who the internal users are, and most of the users are like traditionally all ML development is being done by MLEs and data scientists, which are who are more proficient with Python. But of late, since we are democratizing AI development at Intuit, we have basically software engineers also developing ML applications and deploying ML models and integrating ML models into their applications. So we have a lot of software engineers who are coming from a traditional Java background. So those are the two that we think is important to support, so that we could democratize AI development and accelerate development across Intuit.
Great. And I think I saw GraphQL there at some point, right?
Yes, GraphQL is our feature serving layer.
Yeah.
For basically, once features are persisted in our online store, obviously we don't want users to access the online table directly, and the serving layer will help us, will provide us great benefits. One is in terms of access control, but also at the same time, because it's GraphQL, you could
we've seen mostly REST and gRPC, and I'm curious, I guess, why GraphQL?
Yeah, so GraphQL will, because it becomes more flexible in terms of which features you want to query, how you want to query. It provides some additional aggregation functionalities that comes out of the box with GraphQL. We could do parallel queries. So I think it makes it easier because we want the system to be dynamic as more feature sets are created and onboarded. We don't want to go and update the API and make a release every time. But with GraphQL, we can update the schema and deploy an updated GraphQL schema when a new feature is onboarded. So that makes it highly scalable for us.
Fascinating. Thanks, guys. It's been really educational, and good luck with the next phase of your journey. And if you can jump onto Slack, I hope there'll be more questions for you there. And we're going to take a break. So this is going to be a commercial break. So you may know that this conference is being sponsored by HopsWorks, and HopsWorks is a data for AI platform at Feature Store, plus a full MLOps platform. But we recently moved HopsWorks to support Kubernetes. So now you can install HopsWorks with just a command line if you have Kubernetes installed in Helm charts. There's a new startup license, and there's obviously then a trial license. So we're going to show just a quick, show you how to actually do this, and it'll just run in the background. We'll send out a mail to people who've registered to the conference, so you'll get the details for how to do this very soon. But just to give you a quick idea of how to get up and running with HopsWorks in your own cluster, in your own data center, as quickly as possible. But see you all back here in 10 minutes.
Hello, this is a short introduction to the HopsWorks installer. This is a small script, a Python script, that is meant to simplify the installation of HopsWorks on Kubernetes. Evidently, you will need to have an infrastructure running already on one of the main cloud providers, so that would be AWS, GCP, or Azure, or also available to you would be to deploy it on some sovereign clouds. At the moment, we support OVH, and we will extend that support to other infrastructure cloud providers and such as time goes. So let's dive in. Evidently, I will need to have kubectl already installed on my laptop in my case, and Helm as well. So let me just check if that's true, and that's the case. And if that's the case, I can actually roll my installer. So that's hop deploy .py, and here we are. So it's pretty straightforward. You just need to follow the prompt that are provided to you. In my case, I will deploy on OVH here. For OVH, we will demand you to provide a kubeconfig file. In my case, that will be in this location, and it will check that the file is actually running. We do have two types of licenses at the moment available, one for startups and one as an evaluation license. You will need to choose one, or choose startup, in which case you will be able to review this license and accept it or not. Obviously, not accepting it will stop the installation altogether, but I will go on and accept, provide some information. And here we go. So this information is stored. If you choose to provide other information, that will also work. You provided with an installation idea that's useful for us to be able to help you debug if you have some issues, and the installation should start going on its own. So this will essentially get the Helm charts from HopsWorks. It will set up the namespace, and it will start the installation. We recommend that you have Lens or equivalent installed already on your machine, so that you can preview or review the installation process as it starts. So slowly, here goes. HopsWorks should start to appear, and you should be able to review all the pods that are slowly getting installed on it. So we will see that. HopsWorks installation, typically, depending on the infrastructure that you will try to spin it on, will take about half an hour, sometimes a bit less, sometimes a bit more. You shouldn't have much problems in terms of running it on any sort of environment, but we'll get back to that. So the installation will continue rolling. Let me look at the script. And you will have a status of the number of pods creating. You should reach about 100 until it gets to the next step. So that will be the setup of the ingress, so that you can actually access the deployment. And so we'll patiently wait for that. All right, so installation is complete. It's checking the readiness of the pods. This should take only a moment. And so it is. The external IP has been set, so the ingress address has been found by the script. You have two choices at this point. You can actually set up your script yourself, or you can let the script do it, which I will. If it doesn't have sudo access, it will ask you. Again, it's recommended to actually do it yourself, but I'm a bit lazy, so I'll just let the script do it. Up, and here we go. So it has updated the host's file. We have a default login and password that is the default for HopsWorks, and in theory, if everything runs perfectly, I should be able to access HopsWorks via that link. So let's go there. It's not HTTPS, obviously, so I will just proceed like that. Set up my passwords and name, and here I am in HopsWorks. So yeah, that's about it. You have a full working HopsWorks environment, which you can use for testing purposes or POCs or really small deployments in a startup environment, and you have access to the full AI Lakehouse capabilities and MLOps capabilities that HopSource offer right away. We will simplify that script and the setup as time goes, and you should all be able to use it relatively soon. So here I created a project, and it's a full-fledged HopSworks. It comes with job scheduler, a Jupyter environment, and so on. It also comes with its own Python environment for training, inference, and engineering. You can also install your own libraries, get your own Git repositories here, and use all the capabilities of the feature store, the model registry, and the serving as well. Thank you very much. Have a great time.
All right, we're back. If I can get my video going. So, Chun Hao, you're here. Can you hear me?
Yes.
Great. I'll just introduce your talk. So Chun Hao's at Uber. The talk's on immutable KV store in Cassandra, and he's a software engineer at Uber's AI feature store team based in Sunnyvale and specializes in building large-scale distributed systems. Chun Hao, do you want to try and share your screen? Right, we can see you. Do you want to try and share your screen? So there's a green button at the bottom, share of Zoom. There we go.
Yeah, sorry.
I guess the play button is what you're looking for there in the middle.
Yeah. Can you hear my slides?
Yeah, looking good. If you want to go full screen, I guess play would do that for you if you want.
Okay, yeah.
That's perfect. The floor is yours.
Okay. Hi everyone, I'm Chunhao from the Uber's Mechanical team. Today I'm going to present how Mechanical team resolve a data availability issue while using the Cassandra as the key store to serve the online features. At the beginning, I will give an overview that how Mechanical used the Cassandra to serve the machine learning feature and what's the issue of using the Cassandra that way. After that, I will give a concept of the immutable star that we are using the immutable star to resolve the issue. Then I'll give a deep dive that how that concept will work. First, let's get into the overview of our old architecture. For the Michelangelo, customer will run the daily feature generation to generate the machine learning features. And the features will be read into the Hive table. That is our offline store. And my control team will own a pipeline to do the data ingestion. It will ingest the data from Hive table to Cassandra table. The Cassandra table is our online store. Then for the feature store team, we have a plugin into the inference server. So when the customer send request to the prediction request to the inference server, our library will try to help customer to find the feature that for this feature which Cassandra instance it is in and which table to fetch. Then for the Cassandra table, we will have the UUID and timestamp as the key. Well, typically, customer only want to query the UUID, but we add the timestamp for some reasons. Like by adding timestamp, the new row of the ingestion of the same ID, it won't override the old rows. And we will rely on the TTL to delay the old rows. And with the timestamp, we can also filter the data by the timestamp to always get the latest row, even though for the same for the injection of the same date, we can repeatedly run. And even for now, we can run the injection for very old data. And with the timestamp, we can always select which is the latest one very quick. But they also have some drawbacks. The longer TTL will require more disk. So if you have a very large table, then you cannot set a TTL to a very long time. It will consume a lot of the disk. Yeah, by using Cassandra that way, we are seeing the issue. The largest issue we are seeing is that we will see the data expression outage. As I see for the large table, we cannot set a longer TTL. But the main reason for this data expression outage is that we have the write and deletion, they come out of sync. The deletion is done by the TTL. There's no delay for the deletion whenever Cassandra instance is still running. But for the data ingestion, it's done by a periodic pipeline that can delay for many reasons. For example, the ingestion itself can fail. Also, the data may delay, like customer run a pipeline, and before their pipeline, there are also some steps to prepare the data, and there's a long procedure. So they're likely that we will see some delay for that. And if nobody try to fix it, eventually we'll see that the data keep deleting by the TTL. Well, no new data ingested into the Cassandra. We'll see eventually no data will be served. Customer get nothing, then their model performance will be downgraded. Let's introduce the concept of the immutable star. Well, immutable star will no longer rely on the TTL to do the data deletion. Instead, for each ingestion, we will ingest into a brand new table that is different from any of the existing tables. Then the ingester will also do the deletion to delete the old version tables. To support this concept, we introduce a metadata table for. We introduce a metadata table. The metadata table is stored in the same Cassandra. We create a dedicated key space for the metadata. And for this table, it will contain the key space and table name that we don't require that exists. It just become a virtual concept for the customer. And the customer will query the key space and table name, but we'll do the some conversion for that. Then for each ingestion run, we'll have a different run ID. And the data timestamp will describe the data. Then for each ingestion run, it will have a created timestamp. That is when the ingestion start. All of them will be the key for the metadata table. Then for each row, we'll have a version name for each of the data ingestion. They will create a different version table, and the name will be recorded here. Also, we'll have a status for each of the ingestion. For this case, we'll have 3 entries in this metadata table. The version 1 is already deleted, and version 2 and version 3, they are all completed tables. Each of them will point to existing version tables, and the data timestamp they should match. And the data ingester is the writer of the metadata table. It will maintain the it is the only one to maintain the metadata table. For each ingestion, it will try to create a new version table and update the schema table with the new version table as a new row to that metadata table. Then it will read the data from Hive and ingest into the Cassandra. It is the same as before. Then after the finish of the data ingestion, it doesn't matter if success or fail. We'll always launch a new task to recycle the old version tables. The recycle will include the old computer version. We can configure that how many computer versions we want to keep. Then we'll keep only the latest X versions. The older one will be deleted. It will also try to recycle the previous failure ones. For any cases, we don't need them. Let's have an example. Like for this case, we say that we want to keep the latest 2 computer versions. So that's our start point. But now we have 2 computer versions. Version 1 is point to a table with timestamp 1000. And the version 2, it comes with a timestamp of 2000. And the ingestion starts. It writes a new entry to the metadata table. It's supposed to create a version 3. Then the initial status is pending. Then it creates a table of table 1 version 3. The timestamp is 3000. Then it keeps writing the data to the new version table. Upon the ingestion finish, it tries to update the metadata table to say that for version 3, now the status is completed. It is ready to serve. Then it starts a new task to do the deletion. We said we want to keep the latest 2 versions, so the version 1 right now is no longer needed. So it tried to delete that one. First mark it to deleting, then to delete the table. After table deletion is done, it mark the version 1 as deleted. Now we have 2 versions remaining, the version 2 and version 3, and each of them point to actual version tables with data. And Cassandra client is the reader of that metadata table. It will maintain a in-memory map between the table name and the version table name. For Cassandra client, it will prefer the computer version. It only reads from the computer version, and it prefer the computer version with the latest data timestamp. And if multiple row of the same data timestamp present, which means we run the ingestion for the same date multiple times, then it will prefer the one with the largest created timestamp. For this table, I don't give any data for the created timestamp. And the control can will periodically query the metadata table to update the map. For now, we use the 10 minutes as a period. So you expect that the table translation will be finished within 10 minutes. Then when customer queries the original table, the table don't have to exist. Our customer client will do the modification. It will replace the original table name with the correct version table name. Let's go over some situation. Like for example, for here, we are having 3 versions, version 1, 2, and 3. Version 1 and version 2 is completed, and version 3 is pending. So for customer client, it will try to pick the version 2 as the one to serve because it comes with the largest data timestamp and it has a status for completed. And after the new ingestion success, it will say now the version 3 has the largest timestamp with the completed status. So it will translate the serving version to version 3. Yeah, that's all. That's all my presentation.
Thanks. That's fascinating. Let me get my video up here. This is fascinating. I have a question. All problems can be solved with an extra level of indirection. Is your metadata table also in Cassandra? And then you need to make transactional. I guess you need to make transactional updates.
Yeah, I think for the update, we'll have a less bit transaction for the update. Yeah. Rest of the things we'll try to resolve it by the order of the operation. Because for example, we always safely moving forward.
Yeah, and then stubborn delete of the version tables. Then a question I think about, one more question I have about the TTL. And in streaming platforms, we have both ingestion time and event time. And I guess your TTL is for event time, am I correct?
That's the event time.
And if you supported
sorry. The ingestion is for the event.
Yeah, so the TTL time is for event time.
Injected into the Cassandra.
Okay. But then adding an event time and an ingestion time wouldn't help with your TTL issue?
No, it won't resolve. Anyway, the counter will start. Anyway, the counter will start from the time you ingest the data into Cassandra. Okay. And if no data is ingested, after all data.
But the data gets empty. Okay, right. I get your point. Yeah, I understand. Chun Hao.
Yeah, thank you.
If you have more questions, please the art in the space. So take your chance now to welcome Arjit Jain from TurboML platform. Their machine learning platform will leverage fresh data for machine learning. Arjit Jain is the co-founder and CTO of TurboML, where he's building an ML platform reinvented for real time. He was previously working at Google, building large-scale systems for cloud networking, and he's also published several research papers in top ML and systems conferences. Welcome, Arjit.
Thanks so much, Jim, for the great introduction. I'm Arjit. I'm the co-founder and CTO of TurboML. Really excited to be here. Today, I want to talk about TurboML's platform and how we're able to leverage fresh data for ML. So let's get started. So first, let's define what fresh data means. So there are multiple different definitions for data freshness out there. The way I'll define it is, it's the delay between when your data is created and when it can be used in your application. So then naturally, fresh data for machine learning would mean, how do you make your data with a given freshness accessible to your machine learning system? For example, here could be, I'm able to use the user's latest transactions and behavioral data to detect fraud. Now, the way most teams use fresh data for machine learning is via features. So you can use your fresh data to update features. You can define on-demand or aggregation-based features. And then, depending on the logic and the freshness level that is required, you can decide on a mode of compute. So whether it is on-demand or asynchronously using a streaming-based computation. So an example here would be that I define a feature like an average transaction amount for a given user in the last 30 minutes or something like that. Now, is that all you can do with fresh data? Absolutely not. Even though most teams currently use fetch data for features, and it can provide very good context about the real world to the models themselves can still be outdated. So just for context, the best teams who are using fetch data for features, their feature freshness is in the order of a couple of seconds or a minute. However, their model freshness is somewhere in a few weeks or even months, which is very, very outdated. Now let's motivate why or where you might need a fresher model. So one use case that we're working with a financial institution is around fraud detection. And here what we're seeing is, so labels and new information is very, very scarce, especially for somewhat newer evolving fraud patterns like money mules. So in these scenarios, what you need is to be able to incorporate learnings from this very little data and use that to detect and prevent similar frauds as soon as possible. So the only way you can do this is by improving your model freshness. Another use case is recommendations. So this is different from the fraud detection use case. Here, the challenge is that the setting itself is very non-stationary and highly dynamic. So even though real-time features can help you capture local context about what a particular user is looking at or what they're browsing, what they might like, you still need to capture global trends. So a particular segment, what are they interested in? Again, the solution here is by improving model freshness. So if we summarize this, fresh data for machine learning beyond features can be in multiple different ways. Machine learning itself is highly data-driven, and you can use the fresh data to update ML models in different scenarios. You can improve deployments. So most ML deployments are not a one-off process. You have model selection, model calibration, drift, data quality, all those other processes which require fresh data to continuously improve. And you can also experiment and iterate faster. Now let's look at how you can actually implement something like this. So since we talk about model freshness, let's see how you can improve model freshness. Suppose I'm targeting a model freshness for 1 day, right? And suppose that I want to train a models on the last 6 months of data. Now a naive approach for this would be I have daily retraining job. However, there are a couple of limitations. The first one is if I have independent training jobs, I might modify the code at some point, and the whole process is likely to be bug prone. The second thing is it can be very, very resource intensive. In fact, if it takes longer to train my models than my targeted freshness, then it won't even work. So for example, if I'm targeting 1 hour freshness, but my model training takes 2 hours, then it won't even work. So how can we solve this? We can actually drop parallels between what we already know, which is feature computation, and model retraining. So let's consider the following feature: average transaction amount for a given user over the last 24 hours. And this feature needs to be updated or computed every hour. Now, the same approach that most companies or most people here would take, compute this feature, will also work for model training. Let's see how. So the way typically you would do this is, for the first time, you will fetch all transactions in the last 24 hours and aggregate them. Now, after 1 hour, when you have to actually update it, you won't do it in a stateless manner where you recompute all these things from scratch, but you will do it in a stateful incremental approach, where basically you are able to update this value only on the changes in the last 24-hour window. This is exactly what we'll do even for model training. So a stateless approach for model training would be that I have my data, I have my algorithm, I use that to train a model from scratch. However, a stateful incremental approach would be I have my algorithm, I have some new data and a model state. I'm using this to make an incremental update on a model state and get updated model state. So for example, if I have a model from yesterday and I have data from yesterday to till now, I can use that to update my model to get a model for today. Taking an example of neural networks, here the state would be the model weight, any pre-process that you might have, and the optimizer state. So if you're having a learning rate schedule, those things will come into place. Now, you can probably imagine that a stateful incremental update here would just be a couple of gain distance steps. But here we can see the issue. So basically, unlike feature aggregations, here the batch size and even the order in which you make computations matter. So for example, let's say I can have 100 online steps, or I can have one step with a batch size of 100, and they'll have very different results. So incremental learning is a separate domain of its own. There are a lot of libraries which can help you, get used to incremental learning algorithms. So River is one of the most popular libraries. Warpal Rabbit from Microsoft is also a great alternative. And Avalanche also deals with continual learning or incremental learning for neural nets. Now, we have a way to update a model, right, incrementally. How do I prepare the training data for that? So here, what you can use is a technique called login weight. So most likely, when you are making predictions for a given data point, you're already computing the features for that. You can store these features, and then later when you actually get the label, corresponding label for this particular data point, you can use that to join with those features, and then pass this to your training bucket or training topic, or however you want to use this for training. The limitation here would be that this does not work for historical data, where if you are introducing a new feature, you might require backfill. So we talk about model freshness, but as we discussed, ML model itself is just one part where fresh data can help. There's also model deployment. So typically when we deploy a model, we have processes like model calibration, performance estimation, model selection, data quality and drift, testing observability, all those different processes. All these depend on data, and all these can be continuously improved using fresh data. Just to take an example, let's say I have a contextual bandit based model selection setup. Here, whenever I get a new label, I can use that not only to update the model, but also figure out what metrics or rewards I want to compute to pass to my bandit and help it choose the most relevant model. So with all that in place, let's look at TurboML at a glance. So with TurboML, you can define different components like data sources. You can define features. This can be defined either using SQL or a high-level data frame or API with Python, UDFs, and UDAs. You can define models. So because these are incremental models which support incremental learning, you can choose from out-of-the-box algorithms for incremental learning, or you can write your own code in Python. You can select metrics. You can select analytics. You can select model deployment configurations like calibration, etc. And you can declare all these different components. The next part is how will these components update? So you can define or choose a method in which you want to update these particular components. For example, the data source can be updated either via pull-based ingestion, where basically I'm pulling it via some connectors from some other source, or I'm pushing events to it via some kind of SDKs, right? Features can be updated. I think this we already know. They can be updated in a streaming manner or in a batch manner, right? Model update is, I think, the new part for most people. So here you can have online training, which means you are able to update the model on every new data point. Or you can have trigger-based updates. So for example, let's say if the performance drops below a certain metric, or let's say if you observe drift in some key features, then you trigger an update. Or you can also have ad hoc updates. So I think we were discussing about GDPR, right? So let's say if I want to remove a particular data point from my model training, so I can choose the checkpoint that was basically just before that particular point. I can pass in ad hoc data, so basically the data from that point without this particular example, and then update my model. So basically, I can pass ad hoc batches of data to update my models, and obviously, I can also choose how I want my metrics and model deployment process to update. Again, streaming versus ad hoc updates. The tech stack that we use with TurboML is shown on the slide. So basically, for real-time data, we're using Apache Kafka as the main protocol. For historical data, we're using Apache Iceberg. For all the stream processing that we're doing, we are using a combination of Apache Flink and Rising Wave, depending on what kind of competition it is. To enable a higher level data frame API, we're using IBIS. And the advantage here is we also get for free all the backends that IBIS supports or will support in the future. For batch computation and retrieval, we're using a combination of Data Fusion and DuckDB, again, depending on what kind of competition it is. Now, in most scenarios, right, like let's say when you're sending ad hoc batches of data, there's a lot of data transfer that is involved. So for that, everywhere in TurboML, we're using Apache Arrowflight as the main protocol to share data. Metadata is stored in PostgreSQL. We are using an S3 or compatible object storage for storing our model version. So this includes both periodic checkpoints as well as any named or stored versions. To implement our login weight, we are using RocksDB as the main KB store. And all our analytics, so basically all the metrics that you saw, all the model selection or other basically analytics that we're doing, all of that is happening on Stardogs, which again uses Kafka and Iceberg as the main sources. Now, obviously, when you're building a new system like this, which is following a different paradigm, so streaming first instead of batch, there can be multiple different challenges. Here I've listed a few challenges that we've solved at TurboML. The first one is around data. So because it's all non-session data throughout, it makes even traditional challenges like data quality more pronounced. The second challenge is around the algorithms itself. So if you're using incremental learning, you can have different modes of failures. Like catastrophic forgetting, where basically you forget old data that you've learned on, or basically you want to make sure that your models are robust and stable enough to be used in your end applications. MLOps itself is considered pretty tough for even a static batch setting where your models are not changing, but it is much tougher when you have a continuous streaming setting where you have a lineage of different model versions. Inference scaling is obviously a challenge for any platform. But here, since the main idea is that you want to make it more efficient than batch retrainings, so you have to be able to do this in a cost-effective manner. And finally, if you're building any platform, there's always a people challenge involved. So basically, whatever you're building, is that intuitive enough for people to actually use or build their use cases over? Yeah. I can see that my time is close to an end, so I'll stop here and take any questions.
Brilliant. Thanks, Arjit. I mean, you have a very modern set of tools there, I think, in your stack. What are the main challenges in pulling all them together?
I think so. Basically, it's a little counterintuitive. Where basically what we found was that if you are able to reinvent this whole system, right, for streaming first architecture, it's easier than if you're doing it like just for one particular segment. Like for example, let's say just for feature computation or just for like the model training part. Because now I can define very clear set of let's say open protocols, what I expect from a feature platform, what I expect from models, from the deployment perspective. Yeah.
Great. Thanks very much. Tun. So Tun Shui from Quix. Are you with us, Tun?
Hello, yes.
Great.
Good to see you, Jim.
Great to see you again. Let's get to it. So Tun Shui is the VP of Data at Quix, where he leads the data strategy and developer relations. He's focused on helping companies imagine and implement their data strategy vision with real-time streaming data at the forefront. He was previously head of data and data engineer at high-growth startups and spent his career leading T-shaped teams in developing analytics platforms and data-intensive AI applications. And in his spare time, he likes to go surfing and he likes to play guitar.
Hey.
Same as myself. We've a lot of shared interests. And then he tends to his analog cameras. That's where our overlap ends. Go for it and see where you can, if you can get your screen sharing going. You're there already.
Yeah, I'm going to try and make this work first time.
Oh, no bother. We're good to go.
We're good to go. Okay, fantastic. Okay, hey folks. I hope you're enjoying the summit so far. My name's Tun, and I'm the VP of Data at Quix, which is a Python streaming data technology company. Thank you very much for joining this talk. It's called Enabling Low Latency Fraud Detection with Real-Time Feature Engineering. So I'll aim to have these questions answered for you today in the next 15 minutes. What is real-time feature engineering? How can you build it out? And how you can achieve low latency? So first, a quick definition of feature engineering. You probably know this already, but features are properties that provide machine learning models with predictive power. They're inputs for models during training and inference, and they're sometimes derived directly from the data, and sometimes they're computed. Let's first understand the traditional type of feature engineering first, which is batch feature engineering. You have data in this pipeline that is processed and written as historical labeled data to a data store. This is read by a feature processor to extract and compute features, and it's written to an offline feature store. These are optimized for high volumes of data, and this is what's needed for model training. You need lots of data. So you're probably familiar with this kind of pipeline, and you might be using a database like PostgreSQL or MySQL to store your labeled data, and you might be using another sort of database or cache like Redis for your feature store. And in your workplace, the processing engine of choice could be anything. The talk of the town is Flink, and you might be using something from the same area like Spark. Feature stores are really good because they decouple feature engineering from models. Historically, when that was coupled, you'd have different variants of logic and computation, which resulted in different variants of features being used as inputs to model training. And then again, you get some variation again during model inference, where there would be different features used that didn't match the features used during training. And this decoupling ensures that there's a central place for features. Like Jim mentioned something about that famous quote about indirection, having another layer of indirection, really good in this case. Let's take a look at the data with the example of fraud detection for credit card transactions. I've taken these example records from HopsWorks synthetic data generator. And if you look at their transaction there on the left, you can see that there's a natural key there. You've got a credit card number, and there's a purchase in a restaurant or a cafeteria in a city in the US. And now if you look on the right at that transaction, you can see that less than 24 hours later, there's a cash withdrawal in a city in Indonesia. So this is a really good, believable example of a transaction that's been labeled as fraudulent. But for the most part, if you take a look at these transactions in isolation, it's really difficult to predict any sort of fraud. So typically, you would enrich this data by joining it with other data, such as profile data, which helps bring better context to the transactions. So there on the right there, you can see some profile data has come in. There's the natural key again, the credit card number. And in a batch pipeline, this transaction data with labels would be built up over time. You'd also update that profile data as it changes slowly over time. It's considered a slowly changing dimension. You'd use this data to compute the features and train a model to achieve your desired accuracy. And here are some of the features that you could compute. Spoiler, a lot of the useful computed features are aggregations. And some of the features, such as the aggregations over longer periods, for example, a week or a month, you may have to process many, many data points, and this can be really time consuming to compute. So that's where you might be pre-computing them and saving them to a feature store. With real-time feature engineering, you have a pipeline that serves real-time inferences. It must run with low latency entirely end-to-end to ensure that the ML model is supplied with the latest features. The data ingestion, the feature engineering, and the feature retrieval needs to happen in real time or near real time. The same example I gave for the transactions data would be flowing through, but of course in this pipeline, the ML model would need to retrieve the features so that it can predict whether a transaction is fraudulent. It may well need to compute features on the fly. For example, if there's a scoring rule that needs to be applied based on current location. The challenging part in a real-time pipeline is that feature engineering part. The other parts like the data ingestion, the feature store and the retrieval, that's largely figured out. So I think teams are still having this feature engineering part of the pipeline be a real challenge. And from what I've seen in customers and in open source, teams tend to prioritize two things here. So the first thing is low latency feature computation. And the second thing is a good developer experience when you're building out that logic. Let's take a practical example and fill in some of the technologies here that we're going to use. So the first one there is Quick Streams. It's a real-time open source data engineering framework. It has a sources and sinks API to very easily connect to various data sources and build out your own custom connectors. And if you're wondering why the logo looks like a Python, it's because it's pure Python. We have there at the bottom there, Apache Kafka. It's a streaming message transport or broker. And the beauty of Kafka is it's a true distributed system that's built to scale for high throughput whilst keeping low millisecond style latency. It's also designed with guarantees around message delivery, reliability, and durability, meaning that you don't get any data loss. And Kafka, it was written in Java, and though it has clients in languages like Python, they tend to be very simple producer-consumer types of applications that you can build. They give you the low-level building blocks, but it's up to you as the developer to build out the high-level abstractions. And for feature engineering, you require abstractions such as window operations and state management. So you need to reach for a more mature library that can handle these sort of common tasks. And that's really why Quick Streams is a good fit in the data and the AI ecosystem. And then on the right, you've got HopsWorks, which you probably know about by now. It's a lakehouse platform with a feature store, and it solves many of the challenges when building out these sort of complex data systems. So considering the transaction and the profile data together, this is how a pipeline could be designed. So at the bottom, you've got the slowly changing profile data. So whenever a user updates their profile, an event is generated and it's streamed into a topic called profiles raw. It's consumed in real time by a profile feature processor that will transform it to generate the features and then store them in the online feature store. And at the top, you've got the fast flowing transaction data. And this would originate from payment systems and terminals, and it's produced to a Kafka topic called transactions raw. It's consumed in real time by the transaction feature processor, and then it will enrich the transaction data with profile data. Again, it may go back to the feature store to fetch the features, and then from there, it will compute new features. These new features are written back to the feature store and will keep that feature store up to date so that when the ML model is requested to make a prediction, it can read the data with the confidence that it will be fresh. for the longest time, you weren't really able to enable low latency through technology choices without suffering some sort of pain. A lot of these technologies like Kafka require complex infrastructure, and the companies, some of whom are on the schedule here, like Uber and Pinterest and Airbnb, these companies, they tend to deploy these big platforms and have dedicated platform teams to look after them. That's changed a lot in the last few years, with lots of new projects and vendors coming in aiming to make real-time data processing accessible for the next generation of data engineers and data scientists. Note that you can't use a traditional database to achieve the high throughput and low latency that's provided by stream processing and feature stores. These are technologies that were built from the ground up with these kind of critical use cases in mind. So going through the list there, if you're choosing streaming data, you've got to choose an online feature store. This will enable you to have consistency between your offline and your online workloads, and that you have fast retrieval. You've got your streaming message broker, so you can choose from something that has, the best ones we found out there are those that implement the Kafka API, so Apache Kafka itself, Redpanda, Pulsar, and use stream processing for feature engineering. If you're already using Spark for your batch workloads, I recommend, first of all, trying out Spark structured streaming. You've also got Flink, and you have quick streams as well for those who are more Python-centric. So Kafka is a distributed system, and it uses partitions. So we know that it can scale horizontally, and it can scale out to deal with higher throughput and higher volumes. But what are the other characteristics of its system design that makes it fast? And it's really down to two approaches. So you've got sequential I/O, and you've got the zero copy principle. So first of all, sequential I/O. So you've got records in Kafka, and they have ordering guarantees. And this is facilitated by Kafka's design, which is to store data as an append-only log. So you've got data that is organized as contiguous blocks of memory, as in they are stored like kind of physically next to each other. You've got modern drives and solid state disks, which are optimized for sequential I/O as well, rather than random I/O. And you can contrast that with kind of like the grid there on the left with random I/O. This is more characteristic of your relational databases. They're optimized for random access because you can never really predict what a user wants to query in that database. So they're optimized for that. Another side note is that Kafka was launched around 13 years ago. It's a long time, it's a lifetime in the streaming world. And during a time of hard disks split with those kind of physical spinning platters of magnetic disk, it meant that sequential, like implementing something sequential meant that there was no disk seek time. So those platters didn't really need to spin much. So what are the implications in our current era with solid state disk drives? I recommend following the link in that image credit to find out more. Zero copy principle. So this refers to the copying of data between the kernel and the application context. It doesn't mean making zero copies. What it means is minimizing the number of copies between those two worlds. So how it actually works in practice is the Kafka consumers will read the topic data directly from the log file using DMA, which is direct memory access. So that saves on some time and keeps the latency low. Unfortunately, it doesn't apply when encryption like SSL and TLS is used because you have to hit the compute layer so that you can encrypt and decrypt. So zero copy principle is one of those things that contributes to low latency, but not as much as sequential I/O. The last few slides, I'll talk a bit about the technologies there that I mentioned, like quick streams. So Quick Streams is an open source pure Python framework. It introduced this concept of streaming data frames. And some of you out there may be familiar with data frames from libraries like Pandas and Spark. It's a very convenient way to create tabular representations of data and manipulate it that way. You can see in the code that there's some simple setup there to connect to a Kafka broker and set up the topics. You create a streaming data frame from that input topic. And what it is it's a data frame that continuously refreshes in real time as soon as new data arrives. You can see that we access the properties as columns in a table, and this makes for a really convenient API for extracting features like via doing projections. And we designed the functions to be named and to behave very similarly to pandas. So they're almost interchangeable if you're familiar with pandas. We've got stateful operations. For example, when you need to maintain a count of credit card transactions, you have access to a high-level state object. And you would use it like a dictionary or a hash, and its updates are backed by a local RocksDB store, and it's also backed remotely to an internal Kafka topic. So this means that in the event of an application failure, you don't have data loss, and you can maintain message semantics such as exactly once processing. There are other stateful functions, such as window functions, available. You use them, for example, when you want to compute a count for the number of credit card transactions in 24 hours. You use them for any sort of aggregation over a time window. And here you can see there's a tumbling window of 10 minutes that has a 10-second grace period. You generally apply a grace period to deal with any late arriving events. You get late arriving events in kind of like the event-driven and Kafka world, because sometimes events are generated, they're slow to be generated. You've got things like network issues. So we always apply a grace period. You can see there that we are using a sum aggregation function, but you can supply your own custom aggregation because we enable you to supply an initializer and a reducing function. This one's my last slide. This is about Quix Cloud. So QuickStream's applications don't require any server-side software. They run anywhere that Python is installed. And the approach that we take is to deploy them as Docker containers. So the Quix platform is a fully managed platform that connects to your Git repositories. It handles CI/CD to build your applications as containers and deploy them using Kubernetes. So all of that's fully managed and abstracted away, leaving you to be able to focus on building out your pipelines without worrying about infrastructure. So the workflow here is to use the Quix CLI to set up your project, develop and test your pipelines locally using Docker Compose, and then deploy them to Quix Cloud. It's been tried and tested by a few of our customers, some of whom are Formula One racing teams. So please do try it out. And feel free to connect with me. So thank you very much for coming to my talk. You can find me on Slack as well. So I invite you to come along, and the whole team's there to support you in your journey. So thank you very much.
Thanks very much, Ton. Exciting to see Formula One being powered by Quix streaming. That's, I'm sure, a challenging application domain. Not one that would immediately spring to mind, but very cool. Thanks. Right. So we'll move on to Varrobank, banking on features. That's I guess a pun. Thanks for that pun, Andrew, in the title. But Andrew Wang is a staff machine learning engineer in Varrobank's ML platform team. He primarily focuses on building the feature platform. He has over 8 years of experience building software and machine learning solutions in ad tech and fintech companies. Welcome, Andrew, and great to have Varrobank. I think we had you here many years ago. This is the fourth incarnation of the Feature Store Summit, but it'll be great to hear on what's happening at Varrobank.
Thanks, Jim, and thanks to everyone for joining my talk today. As mentioned, my name is Andrew. I'm one of the machine learning engineers here at Varrobank. And again, I focus most of my effort and time on the feature platform as one of the primary owners of that part of the platform. So if you don't know much about Varrobank, I'm happy to go through it a little bit. Varrobank is the first nationally chartered consumer tech bank in the US, which means we're kind of, we are our own bank. We went through the whole regulatory process. So every 6 months we get audited by the OCC, but we do maintain a bank charter, and that allows us to have more freedom in terms of what kind of products we're able to offer directly instead of having to go through partners or other banks for our services. We are built from the ground up to focus on the needs of Americans who are striving to get ahead. So a lot of our products are more focused and targeted towards trying to help people who are kind of trying to just to make ends meet, maybe helping them to kind of bridge the gap in between their paychecks and to really help them to start building their savings and to have a brighter financial future. We also strive to combine the agility of being a tech company while also having the security of a regulated financial institution. So we are FDIC insured with all of our savings accounts. So that's really what we're striving to be like. And we've been recognized by a number of different types of lists in terms of being fastest growing company or top fintech companies. If you'd like to learn more about Varro, do feel free to join us at our website, varromoney.com, or you can follow us at Varrobank on social media. So here are a number of products that we do try to offer to help our customers get ahead. The first one is we offer a secured credit card that will allow our customers to build credit as they're using the card. Our high yield savings account has one of the nation's highest APYs. And then we offer two different lending products that we try to get ourselves ahead. The first one is more of smaller dollar amounts
to, again, as I mentioned before, help to bridge the gap in between paychecks. But we do also offer a personal line of credit that can go up to $2,000. So you can see that as we are a typical bank, a lot of the kind of common and typical use cases for machine learning do show up on our side as well. You can see this as lending, risk, fraud detection. We do also have our machine learning efforts going into other fields as well, especially in terms of marketing, trying to find suitable consumer or customers that will be able to join us in terms of our product, how we can improve things, or in terms of operations. And that's more or less looking at like how we're handling disputes with our digital banking representatives. All right, so before I go any further, I kind of just want to talk a little bit more about how data flows within Varo, just so that we kind of have a better understanding there. There are two primary types of data that flow at Varo, and as you can kind of guess, a lot of other companies deal with this. It's batch and streaming data. The batch data typically originates in our existing microservices, and each service in of itself contains its own Postgres database. And of course, within that database, you can have multiple tables. We use change data capture, or CDC, to detect the changes to these tables, and then using kind of a combination of Airflow pipelines and glue jobs, then we are grabbing that data, processing it, and then we're putting it into the data lake. Somewhat similarly, at least in terms of the beginning, is how our streaming data works. So here, the microservice is still generating events, and they are still going into the Postgres database, but into a specific table that we call outbox event. And once again, we're using CDC to detect those changes in that table. And from there, we use the Bezium to then pick up those changes, and other services can then listen to those events and use them as needed. So I didn't include a separate slide for this, but the original implementation of the feature store at Varo before I joined had two different ways of handling it for the batch and the streaming side. And the batch side would rely on having these SQL queries that were written in YAML files in the streaming feature just to handle those. And so it made the barrier for entry relatively high, and it made it pretty hard for people to kind of come in and create features. And so feature creation velocity was low, and we were also, because of that, not able to generate new models as quickly. So for the next version of our feature platform, we partnered with Tekton, which, as you know, came out of Uber and Michelangelo's team. Which gave us the ability to combine our various types of data sources together using the same style of code. You can kind of see here in this graphic that I've included from Tekton's website, you're able to combine the streaming and the batch together, and even take data from the request time and convert those all into different features that you can then use for machine learning use cases. And this really fit in with the goal of our team, where we were trying to democratize the so being able to have it so that basically anybody who knew how to write a SQL query on top of the data to generate their features would be able to come into our platform and start creating new features, as long as they had a little bit of extra guidance on the Python part if needed. And Tekton really stood out to us as a managed service. They had a number of really nice features built in. It was very easy to spin up materialization jobs to generate new feature data. The discoverability was quite nice with their feature catalog that was built into their web UI. They provided feature value monitoring a little along the way, but that really helps us to notice, like, if the materialization job has gone wrong, we're seeing a bunch of null values, then we can go and try to fix the issue before rematerializing the data. And then also they offer low latency feature serving at scale. So this kind of takes us back to how do we use the feature store here at Varo. And you'll see here that there's a lot of overlap with what I had originally put in terms of the machine learning that we do at Varo, maybe with a couple of extra additions here. And one of them, which was relatively unexpected to our team, but a welcome surprise, I would say. And that is for app UI elements. So if you take a look at this screenshot, so this is for, as I mentioned before, our Borrow Advanced product, which is kind of that short-term, small amount loan to kind of bridge the gap in between different paychecks. You'll see here on the screen that these different tiles that I've highlighted in red here, the values that are in those tiles is actually powered by data from the feature store. And the way that you can think about it is that when we create a feature vector for a specific use case within Tekton, it can just be those 4 values. We see this as a way to allow for greater personalization for each customer so that they're able to get the specific values that they need in order to inform them what kind of actions they should be taking on the app in order to increase their credit limit for that particular time period. So whether it's increasing the amount that they're putting in for direct deposit per month, or whether or not they're making on-time payments for their previous loans, or if they're keeping their account balances positive. These are all things that we're able to customize specific to that particular customer. And the nice thing is that we're able to support updating these tile data in near real time via streaming features if needed. So I am going to go pretty quickly through this as well, but I know I have some time. I just want to kind of leave off with a couple of the numbers that we have at this point. To date, we've been running with Tekton for around 2 to 3 years now, and we are at over 1,500 features built at this point. And this is via close to 30 contributors at this point. The number might actually have increased since the last time I updated this. But this is really in line with how we kind of view the feature platform, being able to allow just about anybody to come in. So we've had data scientists, data analysts, and even product managers have come in with some knowledge of SQL. They've been able to build their features and start using them in their own use cases. To date, we've also connected almost 70 different data sources. So these are accounting, data like tables, Kafka streams, and we think that we're just going to keep increasing them as we go, handling roughly 7 million requests per day from our own feature service wrapper that we have around the feature store. And our P99 latency is around 20 milliseconds. So we think that that's relatively quick. If we go down to the P90 or P95, that's 10 milliseconds. One other number that I did not put in here was that we do have a lot of, and so more than half of the feature views that we create that are being used in a feature service are being used in feature stores, as you know. We want to be able to reuse features whenever possible so that we're not kind of reinventing the wheel and potentially getting some inconsistencies between different feature definitions. If we have one fixed definition that we're able to use time and helping to increase model development velocity. And so we're really glad that we're able to cooperate and we're able to allow people to come in and develop their own features and kind of reducing the overall complexity compared to how it was before, and thereby increasing the velocity in our current day. So thanks. I'm happy to take any questions.
Thanks, Andrew. Great to have you talk. And Varo Bank. And you seem to have built quite an extensive feature store. So have you quantified any of the ROI comparing a lot of systems?
We are able to quantify in terms of the number of models that we've deployed. In contrast to before, like some of the models that we had were more rules-based models than actual machine learning models. So today, I believe we're at 6 or 7 full-on models that we're running in production. And the nice thing is that we're able to feed those model scores back into the feature store. It's kind of like a flywheel, and we're going to be able to innovate more and more quickly that way.
Great. I think we're out of time. There's no questions on the chat. There may be questions on Slack. You can have a look there. We have a break now, and don't go away. We have a talk after the break. I was going to talk about how they work with embeddings at large scale, and then we have a talk for minutes, I believe. And yourself, re-energize yourself, and see you all soon. All right, we're back. Last session of the day. We have 3 more talks. Drew from Uber is going to talk about embeddings, computing embeddings at scale, which is going to be a fascinating talk, I'm sure. Rosh are going to talk as well about feature engineering, and then finally we'll round off by Fennel, who have a real-time feature store. So, Drew, are you here? Are you with us? Can you hear us?
Yes. Yeah. Just give me a minute.
Brilliant. I'll just introduce you while you're getting your screen sharing going. So Dhruva Kura is a senior machine learning engineer on Uber's AI platform team in the Bay Area. He specializes in training and deploying large-scale recommendation systems, ad systems, NLP systems, and large language models, contributing to the advancement of Uber's business through machine learning techniques. Everything looks to be great. So the floor is yours.
Okay, can I get started? Cool. Yeah. Hello, everyone. Dhruva here. I'm an engineer at Uber. Today, we'll walk you through our work on embeddings at Uber. Here is the agenda for today. We will start with how Uber uses machine learning. Then we focus on embeddings and how embeddings are trained using the two-tower architecture. And then we will discuss about the challenges we have faced while training these two-tower models and the solutions that we innovated and also we incorporated from the industry. And we'll also look at the architecture for embedding versioning and online serving of these embeddings. Finally, the impact that we had across Uber. Let's just first start with ML at Uber. Machine learning plays a critical role at Uber, supporting both our internal and external facing applications. For example, we use ML for marketplace efficiency, helping match riders and drivers and setting prices and dispatching trips. ML is also crucial for our safety and risk systems, where it powers our fraud detection and incident prevention systems. Additionally, personalization and recommendations are major areas where we deploy ML to improve user experience, like in Uber Eats Home Feed. Uber Eats Home Feed ranking. One of our key models is Uber Eats Home Feed ranking system, which is the first interaction for 95% of our users. Most orders on Uber Eats start on this feed, and we have a very limited space to show the most relevant stores and items. It's critical that we show the right recommendations quickly because the feed ranking has direct impact both on user satisfaction and our business outcomes. And we faced 2 major challenges that drove us to adopt embeddings across Uber. First, our retrieval systems, our retrieval models were not efficient. We needed to retrieve the best stores from thousands of options in under 50 milliseconds. And second, our existing solutions, the deep matrix factorization, that is DeepMF, couldn't scale with Uber's growth. It required over 1,000 city-specific models globally and consumed a huge amount of compute resources. And we have seen the performance started degrading as we scale. We adopted embeddings as a long-term solutions to these challenges by upgrading our ML platform, Michelangelo, to make embeddings as a first-class citizen at Uber. That is, the advantages with embeddings are it offers a better performance and also has lower compute needs. And these embedding systems can be scaled at Uber growth. We first applied embeddings to replace our deep matrix factorization model in Uber Eats Home Feed ranking. This allowed us to retrieve personalized stores in under 50 milliseconds and significantly improve the speed and accuracy of our recommendations. With this success, we built out the entire embedding infrastructure that could be scaled, reused, and extended across other parts of Uber business. Let me briefly explain what embeddings are. Embeddings are these condensed vectors that capture the essential information of an entity. We use embeddings to represent several entities at Uber, such as eaters, stores, items, grocery stores, and geolocations, places, etc. Embeddings have become even more popular recently with the rise of generative AI in the RAG systems. Further, embeddings allows us to replace a large set of features with a compact representations, making them perfect for downstream ML tasks like clustering, ranking, and personalization. At Uber, we wanted to build this large-scale embedding generation system to produce embeddings for various entities across Uber. Today, we will focus how we generated embeddings for 2 key entities, that is, stores and eaters on Uber Eats. And these embeddings form the foundation of our recommendation systems, both in our first pass ranker and second pass ranker, to provide personalized experience for millions of Uber Eats customers. Let's just start with how did we train this embedding model, and also how did we generate these embeddings. To train our embeddings, we used two-tower embedding model, which is a standard architecture for recommendation systems. It helps us to learn embeddings based on the user behaviors like clicks and orders. The model consists of two separate networks. One is a query tower, and then the other is the item tower. The query tower, in the case of Uber Eats, in this tower, we input eater-related information like what were their past reviews for the orders, their spending patterns, their orders, their past orders in the last 6 months, stuff like that. And the item tower, this tower handles the store-related information like the menu, the store ranking, number of clicks or orders, and the pricing information of the store. On the right, you can actually see the architecture of the two-tower model. Each tower generates its own embedding. We then compare them with the similarity functions like dot product or cosine similarity. This lets us rank stores for each user based on the preferences and then interactions that they have done in the past. If we train this model correctly, the model should group similar stores and users together in the same embedding space. For example, we would expect all the Italian restaurants in a city to be clustered together. And similarly, users with the shared interests would be placed near each other in the embedding space. You can see on the bottom left that all the Italian restaurants are actually placed at one corner, and then the Asian restaurants on the other side. Oh, and also I wanted to discuss some of the training challenges that we faced for training such a TTE model. Training embeddings at an Uber scale comes with significant challenges. One of the biggest challenges is the sheer number of users that Uber Eats have, millions of them. If we create an unique embedding for each user based on their user ID, the model would be too big to handle for Michelangelo. We explored several common solutions like hashing, hash tricks, bucketing of the users, but the most effective approach was to represent the users as a sequence of stores that they have interacted with, rather than embedding user ID directly. This drastically reduced our model size. Another optimization that we have done is we applied, we got inspired by this GPT-2 architecture where we share embedding weights between both the eater tower and the store tower. This compressed the model further while maintaining the accuracy. With these two optimizations, we achieved a 100x reduction in the model size, making it much more scalable without sacrificing any performance. Up next, one of the unique, I wanted to also discuss some of the unique challenges that are very specific to Uber. At Uber recommendations are location-centric. What do I mean by that? For example, there is no point of recommending a restaurant in Japan to a user in San Francisco. To handle this, we use spatial indexing, which is nothing but we convert the 2D coordinates into a single geohash. This allows us to fetch only the embeddings for restaurant around the user location. In order to integrate this information into model training, we sort the training data by geohash. So the eaters and the nearby restaurants are grouped in the same batch. This helps us to create this hard examples during the training, allowing the model to learn better and optimize more effectively. Another issue we faced is some popular restaurants get far too many orders, which can skew our training data and then also the training of the model. To address this, we applied the log queue correction inspired by Google Paper, which downsamples these overrepresented restaurants in each batch and thereby balancing the data set. Yeah. And then let's just discuss about the architecture. Here is the architecture on how the embeddings are used in the retrieval system. Let's just first start with the store embeddings. These are the information related to store doesn't change much. So we can compute these store embeddings offline at a weekly cadence and disperse into a search index. And the eater embeddings, these are computed online using our eater tower deployed on our online prediction service. So here is how the typical request goes through. For every request, the query embedding can be computed on flight per request using Michelangelo OPS. And all we have to do is a dot product between the query embedding, which was computed on the fly, with the dot product of the query embedding and the millions of pre-computed item embeddings. Doing dot product at scale is a solved ML problem, as you can use sophisticated techniques like ANNs. Now, let's just powerful as they can be used as features in the downstream ML mods. A feature is data that has a predictive power that can be used as an input for models to make predictions. As we discussed before, embeddings have this predictive capability. At Uber, we disperse our embeddings to our feature store palette. This makes it easy for other teams to access and use these embeddings in their own models with simple config. In our case, it is a two-line change. At Uber, embeddings are now used more than just for the retrieval task. They have been a core feature in many of our tier 1, tier 2 models like Deep CVR, which are key for our customer conversion and engagement. As these embeddings are reusable and servable through Palette, this reduces the redundancy and makes it easy to share embeddings as feature across teams within Uber. To fully integrate embeddings into our system, we introduce a new data type called embedding in Palette alongside other existing types like numerical and categorical features. We have also added support for common transformations that are needed on embeddings like padding, filling missing values directly into Palette to make it much more flexible so that other teams can use it off the bat. This approach has significantly improved the feature exploration and engineering at Uber, as we have found that one single embedding can often replace hundreds of manually engineered features and streamlining the model process. Impact. The TD embeddings enable us to replace 1,000+ city-based models with one single global model. These embedding systems are more scalable, supporting millions of Uber Eats users, supporting multiple sessions, multiple locations, multiple cities. We also significantly decrease the time and the resources required for model training. Before, with our DeepMF model, we needed 200,000 core hours to train a model. Now we just train it in 4,800 cores, 4 hours per week. As the TT architectures are scalable, we were able to train on the longer data range, helping us to improve our optimizing metric, recall it 500 by 17%. And finally, I would like to take a moment to acknowledge the team behind this project. This work was a collective effort. It wouldn't have been possible without all their contributions. And yeah, that's it from me. And thank you. Yeah. Oh, yeah. If you guys have any questions.
Fascinating talk. I can start. I mean, we're at HopSearch. We also added embedding as a feature type this year, and I think other feature stores have done it. Do you think that's a core part of a feature store now? A feature store in the future should have embeddings as a type, but also should support similarity search. What's your take on that for the platforms as a whole?
Yeah, I think that's a good question. So we already use the similarity. We already have the feature, which is a dot product or the similarity as another feature. So you have embeddings, and then the similarity is also as another. And if you similarity is just another numerical feature. So it's already supported in Palette. But the most interesting thing that we are working right now is working on embedding monitoring. That is something that we are focusing on because these embeddings have a version associated. Yeah, you're working on the embedding monitoring.
Very interesting. One of the points you made about the representing users, because you have 100 million users or more, that you couldn't have user-specific features. So what you did is you represented users as a list of recently visited restaurants.
Yes.
Is there a bound on that? Was it like 5 or 10 most recent visited, or is this a pattern that you'd seen, that users who tend to go to the same restaurants tend to be similar types of users? That was an insight, I think, maybe that helped, or what led to that insight?
Yeah, I think right now we use because these TD models can be scaled to are scalable. We were able to use 1 year of their past interactions that they have done. And then also we introduce this cross-attention layer, which essentially looks at gives a certain weightage to each of these entries. So we brought in some model architecture changes also to how you can process this list feature that is a replacement for the user ID. So you don't need to. You can incorporate the seasonality, the meal period, and everything into that information. So we have done that on the model side.
Yeah, so I mean, you're effectively clustering users to reduce the state space of users, I guess.
Yeah, essentially we want to reduce the embedding table size.
Fantastic. Yeah. It's been really, really fascinating. Thanks a million for joining us. And it'd be exciting to follow all your work on monitoring of embeddings as well. I think that's something that maybe could be a topic for next year. Who knows? Thanks a million, Dhruva.
Yeah, for sure. Thank you.
Right. Moving on. 2 talks left. Not long left now. So we have Vishaka's on the line. We have you here, Vishaka Sharma from Roche Diagnostics. So this is the first time I think we have Roche talking here. And she's going to talk about Roche's data platform and how it accelerates feature engineering through Gen AI, which is very exciting. Vishaka Sharma is a senior principal data scientist in Roche Diagnostics Information Solutions. She leads advanced analytic initiatives such as NLP and ML to discover key insights, improving the NAVA 5 product portfolio, leading, of course, to better and more efficient patient care. She's authored 50 plus peer-reviewed publications, had 25 invited talks, is a senior member of ACM and IEEE, and a fellow of the American Medical Informatics Association, and she holds a PhD in MSc Computer Science and B in Computer Engineering. Great to have you, Vishaka.
Thank you, Jim, for the introduction. I will start sharing my slides.
Please do, yeah. We're looking good. So the floor is yours.
Thank you. Yeah. So hi everyone, my name is Vishaka Sharma. I'm a senior principal data scientist at Roche Diagnostic Information Solutions. And today I will be presenting on the topic how Roche data platform accelerates feature engineering through generative AI. So to give you a little bit of a background of Roche, basically Roche is a 126 years old global leader in biotechnology and in vitro diagnostics. It is headquartered in Basel, Switzerland, and it has 2 main business divisions, diagnostics and pharmaceuticals. So as the future of healthcare is tied to digital transformation, Roche has developed impactful health innovations benefiting millions of patients. They lead in vitro diagnostics, performing like 27 billion diagnostic tests, and a top provider of cancer treatments with over 16 million patients treated with Roche medicines. So Roche basically last year has unified its digital solutions under the brand Navify, which integrates data across care settings, deliver insights, and accelerates healthcare innovation. And you can find more information about it at navify.com. So just to give you a little bit, we are in the process of basically building this digital data integration platform, right? So what the goal of this digital data platform integration platform is of healthcare data, which is sitting in electronic medical records, digital pathology, radiology, and clinical reports. It could be clinical notes, it could be diagnostic reports of various types, right? To empower the research, clinical decision support, and healthcare insights through Navify products, ultimately improving the patient care. So I think one of the things that I want to also highlight is that, just to see like basically our journey started few years back, I will say, in this digital products. And then our goal was to build some NLP systems, which are basically based on convolutional neural networks in the past, right? So as most of this healthcare data is unstructured and is not available for quick assisted data abstraction solution, right? It leveraged basically the natural language processing, machine learning to auto-detect medical concepts and translate these free text into data that is structured and enriched while reducing the burden of manual data entry. At that time, when we started a few years back, we were using, deep learning models like convolutional neural network, BiLSTMs, etc. So to go through a typical machine learning NLP pipeline for feature extraction, etc. But recently, what we are doing is as we are all exploring the large language models and generative AI, one of the recent capability that we have building in our data platform is that we are working on automating a case summarization for tumor board meetings where the clinicians come together and they discuss the different cancer cases, which are quite advanced in their clinical journey, right? And for these, we are leveraging generative AI. So this capability is delivered through Clinical Hub, and it basically aims to automate the synthesis of patient data from various unstructured sources, such as PDF reports, and creates a cohesive and comprehensive summary for these tumor board presentations for the clinicians, right? So by doing so, we save some time and ensure consistency and accuracy, right? So these AI generated summaries are shown on the left and the original source of documents are shown on the right. So users can easily edit the AI generated text to match their preferred documentation style or regenerate the summary if needed. So the hyperlink reference numbers allows us to quickly directly access the original source for each specific data point, ensuring there is a transparency and easy verification. And for all these processes, we always have a human in the loop because we are highly regulated healthcare industry. So we have to make sure about the transparency and the easy verification throughout this AI ML pipelines that we are building. So to give a little bit more context, the problems that we are trying to solve here is, as we all know, the cancer care healthcare data is very extremely complex, right? And the patient has its own journey, right? So in this slide, what we are trying to show you is that in 2014, let's say the patient was diagnosed with breast cancer in the right breast stage 2A with certain positive and negative biomarkers. A lumpectomy was performed in 2015, and in 2019, the cancer relapsed, spreading to the liver, and was classified as stage 4 in 2020. There was another relapse, right? So, with cancer spreading to bones and liver again. So, the NCCN, which are the clinical guidelines, they recommend the treatment that should be followed for these cancer patients, that also recommend going through certain clinical trials for the best treatment options that could be available. So, if you look at this patient journey, all these data elements, mostly they are sitting in unstructured notes. And if we have to extract to get some quick clinical decision making for the clinicians, it's a very daunting task. And it's a right problem to solve using NLP, large language models, Gen AI, depending on the use case that we want to follow. So now, based on this, like our teams in Roche, they definitely identified that, we have these data that is sitting in diverse reports. It also has multiple languages because Roche is a very global company where, this healthcare data and concepts are not very clear, and harmonizing this data, mapping to certain terminologies and healthcare standards, while also analyzing and exchanging this information using different for different use cases, right? So for example, healthcare data has its own data dictionaries, synonyms, abbreviations. So manual annotations is always very labor intensive and subjective. A lot of these documents also exist in PDF formats, right? So we all agreed that we need certain capabilities in our data platform which can handle optical character recognition and these NLP techniques to extract these entities for these patient records. So one of the use case I just want to go through for this talk is that, for example, in cancer, right, we have a different chemotherapies that are given in which, and the information is provided in different clinical notes. And what happens is that individuals basically go through different drug administrations and we call them as chemotherapy events, right? So these has to be extracted and mapped to the proper medication and the terminologies, right? So in this case, each event must be assigned to a time extent based on the date of the note or any temporal modifier or and indicators like time expressions identified alongside the medication event. So what we did is we also are very much collaborative with academic principal investigators. And also we participated in this NASAL challenge that was in 2024 that also provided us access to the data that was de-identified from various different academic centers in United States, right? So for this sheer task, what we did was our goal was to advance the state of the art of this clinical event timeline extraction from these electronic health records. Specifically, this work was focused on chemotherapy events, right, from these electronic health records for patients which were diagnosed with breast, ovarian, and skin cancers. So a subset of the patients were annotated for the gold entities and time expressions, temporal relations, and patient timelines. The rest was basically the unlabeled data. So there were basically two subtasks that we went through. One was, the gold chemotherapy event mentions, which are highlighted in green. and the time expressions, which are highlighted in blue, that were provided along with these electronic health records, right? So the goal was for us to build these patient level timelines using the gold annotations as input, right? And so this task, basically, the first one explored the topics of temporal relations extraction and timeline creation if event and time expression input is perfect, right? And the second subtask was, which is basically the realistic real world setting that only electronic health records are provided. And that task, we have to develop an end-to-end system for chemotherapy treatment timeline extraction for this patient's electronic health records. So this was how the data set looked like for us. And it's a very typical healthcare data set, right? Like where we have a different kind of unstructured PDF or text format free notes like radiology, pathology notes, right? Discharge notes, etc. So a subset of the patients we sampled to create the main experts basically created these gold annotations for these events, right? Then basically a typical machine learning pipeline, we divided the data set into training, development, and the test sets. And this table basically is showing you that, how the number of the patients, clinical notes, and words across these training sets, friend sets, right? So in the words refer here is the tokens separated by these white spaces, basically. So after that, this is, I will say, our main large language model pipeline looks like for us, right? So what you see here is that, we leverage current state of the art large language models because earlier we were using very deep learning methods like convolutional neural networks, right? But now with this large language models, we started looking into the Mistral and the Llama 2 basically, and start doing the experimentation on different sizes and the architectures basically on the token sizes. I have given a reference because we have published this work also where we can find more details on what those configurations look like for us, right? We went through the basic data processing steps basically, which is like paragraph detection, documenting, chunking, etc. To make it very simple, we just use these out of the box shelf models and then tried just the zero shot prompting, right? So even with these models, basically our our rank was 5th basically for all the participants who participated in this challenge, right? And then we were able to create these chemo timelines based on this data set. And these de-identified academic center patients, but then, this kind of a feature we are in the process that we can implement hospitals basically to structure their data and make some clinical decision making out of this kind of an LLM pipeline that we are trying to build. More details can be found in our publication, but just as an example, I also want to highlight, right? We are also using very healthcare specific large language models, Labs, MedLlama 3, which basically has which also uses like very healthcare specific embeddings from different healthcare data sets, like, PubMed articles, etc., which are very domain specific and which are highly accurate and also very much production ready, that can help us improve the accuracy. And that is something, the ongoing work that we are exploring, that how do we leverage these models, which are much more that can give us better results, so that verification and validation basically for us. This is just a code snippet, that has been we use basically for basically creating these prompts and then running these pipelines to basically apply these large language models for us. To keep it, also I want to highlight, right, basically, Roche, as I said, right, is a highly regulated industry because of healthcare, for diagnostics and pharmaceuticals, right? So we also realize that, all the NLP and the machine learning that we do, there is it has to be basically, the goal for us is to maximize the benefit for the patients, but also minimize the harm that can be done, right? So in early 2023, before taking on these projects, right, we have also adopted some 13 public-facing Roche data ethics principle to guide our data handling behavior that we maintain throughout our platform while creating these pipelines, right? And then these are the clear set of principles that we follow for design, development, deployment, and monitoring of our AI solutions. So I mean, just in the conclusion, I will say, building these kind of LLM platforms is a journey for us, right? And building these can come with significant challenges, right? Including the high cost if we have to build something from scratch in healthcare domain. And there is a need for specialized talent, infrastructure requirements, right? And they require careful pre-processing since inputs may not always align with their intended purpose, right? Privacy and legal concerns in the healthcare data is also very critical because of GDPR and HIPAA regulations. And additionally, these LLMs can suffer from algorithmic bias and may generate inaccurate information leading to misleading diagnostic recommendations or false treatment suggestions. So despite these risks, LLMs can effectively summarize vast amount of data. And that is a small feature that I think I spoke in the beginning of my slides, that we were able to create that feature in one of our solutions, leveraging the platform, right? So now to ensure that these LLMs platforms are developed and used ethically and responsibly, we are a team of multidisciplinary professionals like clinicians, peers, lawyers, regulatory experts, and computer scientists who play a very critical role in this building these end-to-end platforms, right? So it's a tremendous opportunity, but also a tremendous responsibility, especially in this healthcare domain. So this will be a journey for us, I will say. I would like to thank the audience, and then, we are a team of software engineers, data scientists, product managers. And then, yeah, I mean, Roche is hiring. Thank you.
Thanks very much, Vishaka. There's a question in the Q&A if you want to try and type an answer in there. I think we might be able to do that. We got to move on. Thanks very much. And we have the final speaker of the day from Fennel. He's going to talk about data quality and feature quality and how to maintain that in their feature store. It's Nikhil Garg. He's the co-founder, CEO of Fennel, a real-time feature store built by an ex-Facebook team. Previously, he was at Facebook, where he led teams behind PyTorch. And in a previous life, he was an avid competitive programmer and represented India in the world finals of the ACM ICPC twice, which is pretty impressive. Nikhil, are you with us? You were with us. Yeah, you're unmuted now.
Hello. Hey, folks. Hey, Jim. Hey,
Great to have you back again. Do you want to try and share your screen, and we'll see if we can get that part going?
Absolutely. Do you all see my screen?
Okay, go for it.
Wonderful. Thanks, Jim, and the rest of the team for having me back. Wonderful to be back, second year in a row. As Jim mentioned, my name is Nikhil. I'm the CEO of Fennel. Fennel is a modern real-time feature engineering platform. And today I'll be talking about data and feature quality and what we do for that in our platform. A bit of history about Fennel. So as Jim mentioned, early on in my career at Facebook, I was closer to applied machine learning. I was running a group of 100 or so ML engineers. And my team used to use various ML infrastructure tooling built by Facebook, and used to run into all sorts of issues with some of them. In the second leg of my career, I was working on PyTorch, building this time ML infrastructure, but not just for Facebook, for the rest of the world as well. And both of these were transformative experiences. The first one taught me a bunch of things about things that actually matter in practice, and the second one told me the importance of building high quality platforms and really good developer experience that PyTorch is known for. I, along with my other, some Facebook colleagues, started Funnel, and the moment we did that, we got a bunch of support from, who's who of industry. People like Adam, who was ex-CTO of Facebook and is on OpenAI board, Kevin, who's CPO at OpenAI, Neha, who's one of the three creators of Kafka, Mikhail, who was CTO at Yandex and recently was running Bing under Satya Nadella. People that credibility started their network to us, and between our network and their network, we have scanned hundreds of companies and mapped out the full space of problems people run into when feature engineering is involved. You have probably heard about most of these today from other speakers. They are ease of authoring a feature, especially with real-time machine learning, data and feature quality, reusing features, catalog discovery, compliance, cost, all of those things. I will not be touching most of these. Instead, my focus today will be on data and feature quality. So let's maybe ask ourselves, why are we even having a discussion about it? My experience, which I have now since validated with a bunch of engineering leaders across the industry, is the moment you are running at scale, and by scale I don't even mean Facebook scale. I mean the moment you have few models being trained at any point of time, 3, 4, 5% data science team, some real-time components as well. Something or the other is always failing. Your pipelines aren't working the way they're supposed to. Something breaks, and then models don't perform as well as they were supposed to. When you trained them, or they used to work well, and then all of a sudden they started regressing. Real story that I was once upon a time was running video search efforts at Facebook, and I was running a team of I think 30 or so ML engineers at that point of time working on video search. And the single most impactful launch my team had line was setting a feature to -1, and was basically not a improvement we saw across an organization of 30 people, and they show up in real business metrics. But unfortunately, for most of the in-house systems, these are an afterthought. When we built Fennel, we knew from our experience that this needed to be elevated to be a top-level architectural goal, and so we laid in 8 pillars of data and feature quality. And our approach, we literally enumerated all sorts of outages and issues we had seen in our experience at Facebook. And for each of them, we asked ourselves, what is an ideal preventive tooling that is not super intrusive, but still prevents you from, making those kinds of mistakes. I'm going to walk you through these 8 next. First off, we have strong typing. We have a strong typing system, optional types, recursive types, generic types, struct types. You can do funky things. You can take a regex that describes a zip code, and then build a type out of it. And at the type system level, you're now guaranteed that this column can only have valid zip codes. And this, extremely simple, goes a really, really long way. It allows us to catch data quality corruption issues right at the edge before they start polluting the rest of the features downstream. So we have strong types, but then our pipelines themselves are strongly typed as well. So in the middle picture here, you're seeing a pipeline, how Funnel pipelines are written. These are very Pythonic native functions. So here you're joining some data set that, and each of these operators gives back a type data set. And if you were to use them in a way that is, types are not adding up everywhere, you would not be able to even commit this data set to Funnel. And so types are present, not only the system at the data level, but the pipelines are strongly typed. And not just that, when you're doing compute, you have the ability to fall back into general world of, pandas. But if you look at the rightmost picture, if you want to compute something, we have an expression DSL, very heavily inspired by Polaris and somewhat inspired by Spark as well. And all of these expressions themselves are strongly typed as well. So for instance, amount half is going to be column of amount divided by 2 as type of float. We know at compile time that this quantity is going to evaluate into float or int or string or whatever. And if you're doing some, or maybe there are some cases where it will be null and your computation is gonna fail. We are able to catch all of these typing issues. This catches a whole bunch of issues. This in itself is like a really big part of our story here. But then we also have native support for data expectations. Here you're defining a Funnel data set. And right next to the data set inline, you're able to describe your data expect. Adapted that to work for both batch and streaming data. And types are, row level constraints, that this is a valid row or this is not a valid row, whereas expectations are distribution level constraints, that some rows out of this range are fine, but not too many of them. Some null values are fine, but not too many of them, and so on. And since we built this on great expectations, and obviously we support alerting monitoring on this, people are able to catch all sorts of other issues. And since it is inline next to the dataset definition, acts as a documentation as well. Versioning and immutability, I think everyone in this room would probably swear to that. Versioning and immutability are really important. The specific issue that we wanted to target through this is a model was trained with some features. Then someone came in, refactored the pipeline, possibly in a good intent, possibly believing that it doesn't actually change the mean distributions a little bit. And now your model that was trained on a different distribution of input features isn't behaving the way it was supposed to originally. To combat this, every asset in Fennel is versioned, as you can see in the first line here, and all versions of all assets themselves are immutable. So you cannot change them even if you wanted to, unless you are incrementing the version. And by allowing you to maintain multiple versions simultaneously, but not mix them in weird ways and keeping all of them immutable, a whole class of production issues are caught by Fennel's system. Next one, this is probably my favorite on this list. It is 2024, and most people who build production pipelines for data using Spark or Flink or other things, most of them are not unit tested right now. And it is unbelievable to me that hundreds of millions of dollars of business is done on these pipelines, and they have no protection against them. And we believe that happens because writing tests for these things is really hard. We made that really easy at Fennel. The way we did that is you built all of our Fennel engine twice. First in Rust in a distributed manner, efficient, and all of those good things. But then second time we built it directly in Python in memory. It is not persistent, it is not efficient, it is not scalable, but has a full feature parity on all the APIs. So here, as an example, you import this mock decorator that Fennel exposes. You're writing a regular unit test. You could have used nose test or PyTest as well. You put this mock decorator here. It gives you a fake client object, and you now have the full power of Fennel. You can create complex data sets, pipelines, put dummy 3 rows in A and that you are getting what you're supposed to get. All of it is completely in memory. You could be on a plane. It would work. All of Fennel's surface area is unit testable. There are no parts of it which you require a real Fennel server for testing. And we heavily encourage test-driven development. Not only it raises the quality of your pipelines and your production systems, it also makes your development workflow really fast. So the way it looks like is you make some change, run a test, 10 milliseconds later, you know it is not working, make a change again, go back, run the test again. And that loop becomes extremely fast-paced. Compare that to writing some code, running a Spark pipeline, waiting 10 minutes, realizing something went wrong, and then going back and making a change. So unit testing is another important pillar. We have compiled time lineage validations. So every time you make a change, you have to describe what you are changing. And at the commit time, Fennel server can reject a whole bunch of changes if something does not look correct from a compile standpoint. So for instance, if someone is deleting a data set that someone downstream depends upon, clearly it is an invalid change, and Fennel will prevent that from happening. And the fact that there's a single engine that is aware of the full lineage end to end across and is able to enforce a discipline, that is really, really powerful and magical. Type mismatches, circular dependency, all sorts of weird issues are caught at this stage. Once again, the compile time before any computation is even done on any of this code. Then we have structured metadata and ownership. Many years ago, I worked at Quora. I was given a job of improving the engineering excellence at Quora, and so very surprisingly, we found that just assigning an owner to every module of code, name is attached to a module. Then they feel a sense of ownership towards maintaining it. If someone is modifying it, there's a clear natural code reviewer for it. If someone is moving on, maybe leaving the company, leaving the team, they know they have to hand over this thing. It becomes a checklist at the exit time and so on. And so all these benefits come from having a human reviewer and other structured metadata flags around tags and deprecated status and so on. And then obviously we tie that in Fennel console and actually give you real utility out of it. You can get real discovery, browsing experiences built on top of that are really powerful. And so there's real value for people to maintain this. In fact, ownership is something that we mandate. If you try to create some feature sets or data sets in Fennel without having a clear owner, that would be caught at compile time as well. Now, this is another very cool thing. It's a relatively recent addition to Fennel. So one common mistake or source of mistakes I saw was, there's a production pipeline. Someone wants to, make a change to that. And so they ideally want to fork that and change that. But there's a whole bunch of things that are just ingrained into the pipeline definition itself. Like where does it read from? Where does it write? Maybe in development, I want to write in some other place and so on. And so people would inadvertently introduce changes in production systems. To prevent that from happening, at Fennel, we built a Git-like branching system where you can have multiple branches. Each branch is stateful. It has data sets and pipelines and so on. You can clone a branch. Now you have a second branch with the same 100 data sets and pipelines, but these are logically independent views. Changes made to one would never impact your data sets and pipelines visible from the other branch. What is more interesting, however, is the branches are copy and write. So when you clone them, the system is smart enough to know that even though these are different logical views, fundamentally they are the same data set. And so I don't need to redo any computation. It simply increments a ref counter in some places. But when you modify one of those 100 pipelines in, let's say, second branch, only compute worth that is now started. The original branch is still unaffected. The remaining 99 data sets are still shared between them. And this workflow makes development really easy. You can now give a branch to every developer. You can give a branch to every project. You can have multiple branches per developer. You take a branch, start some backfilling, clone a different branch, start a different backfilling, go back home, and when you come back tomorrow, both these independent branches are ready for you to do your experiment on. And within a branch, we remember the full commit history of all the changes that have been made to it. Who changed it at what time, we generate commit hashes and summary objects and so on. And so what infrastructure as code does for infrastructure, Funnel does that for data pipelines, where everything is version controlled, and you can exactly know what the state looked like for any branch at any commit point in the past as well. We also do feature drift detection, where for literally every single feature, without any instrumentation, we are tracking its mean, its standard deviation, and generally distribution over a period of time in real time. And so, and then you can set up alerts on this quantity as well. So this is literally the graph for a single feature. And you can see here that the mean, has been well behaved more or less, but standard deviations have become wider compared to what they used to be. And these are the kinds of events that I wish, my team had the tooling for to get alerted in my, prior career roles. So these are the 8 primitives we are building for Funnel. Funnel, in addition to focusing on data quality, has best-in-class developer experience. I'm happy to announce that we'll be releasing Funnel in open source very soon as well. So for those of you who would like to take it for a spin, feel free to reach out to me. My email is nikhil@funnel.ai. And for everyone else, thank you so much for your time.
That's great, Nikhil, and great to hear you're going to go open source. I think it's great for the community as a whole. I think we'd all agree that testing an AI system is harder than testing a classical DevOps software engineering. About feature stores and feature engineering in this conference, but we also have models, and models need to be validated. And then you talk about the operational part of testing distributed, and will that work? Where do you think the responsibility lies? Is it team, or should we train our data scientists to do more feature engineering, or what are your thoughts on that matter?
All fascinating questions. So let me just share my stream of consciousness on this. I believe you're right that testing machine learning systems is harder than testing software. And yet we use that as an excuse. And when I say we, I mean we, the community, we use that as an excuse because in practice, our testing capabilities are significantly lower than that of software. I believe that just closing that gap in terms of a bunch of best practices around typing and unit testing and so on would actually take us quite a bit closer to the ideal promised land, but it's not sufficient, obviously. Then there are other kinds of interesting properties in machine learning systems that are not present in software systems. I think that is where distribution based tests and alerts and those things come into play. I believe that I believe in a pragmatic approach. As an organization, assuming it's a mature organization, just literally take a note of things that go wrong and one by one plug those gaps and do 80-20 and so on, and eventually would end up with a set of practices that are possible, easy to implement, and still end up capturing a whole bunch of cases, which is what we have tried to do at Funnel. I do believe that relying on a different function other than data science to build feature engineering pipelines is a mistake. I think people, data science, every time there is a handoff involved, I think usually there's a loss of quality, loss of productivity, and so on. At the same time, I think we as platform teams need to provide higher quality tools to our data science teams so that they are able to actually do all of this in a more effective, independent manner.
I think we can all agree with that. And I think it's a great note on which to end the conference for this year. Thanks very much, Nikhil, and thanks to all the speakers from today. Thanks to HopsWorks for organizing the event, our partners, Decoding ML, Real World ML, and NumFocus. And this isn't it for the year. If you want to, go to our Slack channel, you can contact some of the people who you've heard from today and other people in the community. We will come out with the videos, and we'll mail you with more information about the talks that we had today. There is a Medium post where you can submit blogs on feature stores. Feature Store community has also a newsletter, and we'd love you all to subscribe for that. And you can follow us on LinkedIn as well. So thank you all for joining. See you again next year, and good luck in making AI a reality.